Yes. I think that. We used to, I think your description is accurate. We used to say, oh, there is not really a. So it's a coexistence of many different landscapes, which means that's essentially no well-defined. So no.
Okay, so welcome to the third day of the workshop. Thanks for your heroic effort in the shop. I did 13 on Sunday. So we have 5 dogs, and including 3 live dogs and the fourth one is in Spivak from Cornell. Fractional Chern and fractional.
Okay. It's okay now. Okay, cool. Well, thank you for coming on Sunday morning, 8:30. I hope you find worth it. And I'll be talking about fractional Chern and fractional topological insulators. I just want to start with acknowledging the people doing the work. The first part of talking about fractional Chern insulator was led by a postdoc and a graduate student, Anton and Zheng Chaoxia. And the second part, the fractional TI, was led by a postdoc, Kai-Fei Kang, graduate student, Boris, and also a undergraduate student, Yichen Chiu. And as many of you may know that we share lab with Excitons at Cornell University. The boron nitride crystal is from the famous Japanese group and its funding sources. But before I actually start talking about the topic, of course, we would like to say that, moiré materials realize almost nearly every phase of condensed matter physics. And it turns out that actually Boris' contribution had footprint in nearly everything we find in moiré materials. For instance, the transport in small gap insulators, the ES variable range hopping, Wigner crystal and stripe phases. In this case, it's under zero magnetic field, but it's very much connected. The electrostatics of the edge states for Chern insulators, electron hole double layers, that this can go on and go on. And I just want to say that congratulations on the amazing over half a century contributions, to condensed matter physics, and happy birthday. So I think I don't need to introduce too much in this audience. The story really starts with the discovery of the quantum Hall effect by von Klitzing. And also later on, 2 years later, the fractional quantum Hall effect by Stormer, Tsui, Gossard, and also the theory provided by Laughlin. And the quantization is amazing, as you heard on 2 days ago, that is better than actually 1 part per billion. It really now provides a standard for the fundamental constants. And soon after this, actually, just a few years later, Haldane actually asked this question whether quantum Hall effect can exist under zero magnetic field. And he came up with the Haldane model in 1988. And I think I don't also need to talk too much about it. It's a imaginary hopping, next nearest neighbor hopping on a honeycomb lattice. And that would give rise to a positive energy gap and a negative energy gap, respectively, at the K and the K prime point of the Brillouin zone of this honeycomb lattice. And that would give rise to a Chern insulator. The band has a Chern number equal to 1. So that can realize actually, so the idea is that instead of applying a large magnetic field to a 2-dimensional electron gas without a lattice, if you can cook up a appropriate lattice with the right amount of a imaginary hopping or complex hopping, then you can actually get a series of flat Chern bands that look quite similar to the Landau levels. And if you put your Fermi energy filling one of the Chern bands, you get the Chern insulator and the quantum anomalous Hall effect as have been predicted. And if you actually put another time reversal copy of this flat Chern bands, you will get the 2DTI or the quantum spin Hall insulator in its simplest form. And that was found by Kay, Malay, and Fu, 2005, 2006, and also by Bernard Hughes and Zhang around the same time. And if you now fractionally field a particular Chern band here, under the right condition that I think Alan already talked about how uniform the Berry curvature distribution is, And you could also realize the fractional Chern insulator that can exhibit the fractional quantum Hall effect under zero magnetic field. And that was first predicted theoretically in 2012 by these people here. And if now you also put another time reversal copy for this fractionally built Chern band, and you can also get fractional TI, a fractional topological insulator that was pointed out by Bernabik and Zhang first, and then slightly more complete theory provided by Stern and Levin in 2009. And so here is the progress so far on the kind of phases that I talked about in moiré materials. Pretty much the short message is actually that CIs, FCIs, TI, FTI, all these phases matter, more or less been realized in this kind of materials. For instance, the first is graphene aligned to boron nitride under very high magnetic field. Andreev Young's group found evidence of the fractional Chern insulator. And also in TBG, twisted bilayer graphene, both about Young and David Gordon, and also Amir's group. Actually, in particular, Amir's group found under finite magnetic field, you can also stabilize the FCI. Also, in many of the TMD moiré materials, you can actually find all these phases of matter. And also very recently, in multi-layer rhombohedral graphene aligned to BN in Long Ju's group at MIT, they also found FCI state in this very new material here. So since that this particular material, twisted multi-telluride, realized almost everything that I listed here. So this talk will be just about this material, the twisted multi-telluride. Okay, so let me just first give you a brief introduction on this moiré semiconductors. The building block is this monolayer transition metal dichalcogenic semiconductors, TMD. This is the crystal structure. If you look from top down, it looks like a honeycomb lattice, just like graphene. And except that the A and the B sublattice sides are not the same. So the inversion symmetry is broken, so that you actually open up an energy gap at the K and the K prime point of the Brillouin zone. So you can just think of it like a gapped graphene with a gap size on the other 1 eV here. And another thing different from graphene is actually that there is a transition metal with pretty heavy mass. And as a result, there is pretty strong spin-orbit interaction. But the spin-orbit interaction, the spin-orbit field can only point to the outer plane direction because of the mirror symmetry in each of this monolayer here. And as a result, we call it the spin is locked to the outer plane, and it has SZ conservation, which turns out to be important later on. So this is the band structure taking into account of the spin-orbit interaction. You can actually see that there's a huge spin splitting at the K and the K prime points. The splitting is opposite, so that it preserves the time reversal symmetry. So you can think of that basically the electrons at the K point or the K prime point, they break time reversal symmetry, but they just break it oppositely so that the entire system has time reversal symmetry. Okay, so similar to twisted bilayer graphene, now very famous, and you can actually produce moiré materials using the same kind of technique. For instance, you can just give it twist angle, and you can generate a moiré pattern with period about 10 nanometer, depending on the twist angle. But 10 nanometer is the range that we are interested in. Different from graphene is actually that you can also use two different materials without any twist angle, but make use of the lattice mismatch between the two materials to produce a moiré pattern. For instance, this particular combination aligned at 0 degree with tungsten selenide, tungsten sulfide. It has 4% lattice mismatch, and that will produce also a moiré pattern with period about 10 nanometer. Okay. So there, just compared to graphene, there's an extra way of producing the moiré lattice. You can actually really see it in a STEM image. This is a STEM image in collaboration with David Mueller's group at Cornell. Looking at this particular combination, which is a heterobilayer that has 7% lattice mismatch, you can actually see that the small dots are the real atoms, but on top of that, you can also see the emergence of a moiré lattice, pretty regular moiré lattice, and that's the unit cell of the moiré lattice. So in the heterobilayer, typically, you know, when you have this a superlattice structure, you form flat bands in the mini Brillouin zone. So you don't really talk about the big Brillouin zone anymore. You talk about the mini Brillouin zone. For the heterobilayer, you have flat bands in each of the layer. For instance, multi-telluride and tungsten selenide. And to a pretty good approximation, in many cases, that you can just isolate one flat band in this kind of heterobilayer structure. And it turns out that in a paper by Allen in 2018, that the low energy physics of this flat band can be mapped to a Hubbard model on a triangular lattice, right, with the T and the U term. So that's for heterobilayer. But for homobilayer, the energy level is exactly degenerate in a two-layer. And so you actually you cannot really isolate just one band. You actually have to at least take into account the first two bands, they are degenerate. And in general, they can hybridize. Okay. And it turns out that both in a paper from Allen and also from Liang Fu in 2021 in Nature Communication paper, that shows that the low energy physics of the first actually the first four bands, the two bands here can actually be mapped in some twist angle to a K-Malay model. And the reason is sort of the following, that each of this band has a one-year orbital that forms a triangular lattice, but together they form a honeycomb lattice. And because they are K electrons, so actually the hopping is imaginary. So it's already a bit looking like the Haldane model. And together with this skyrmion lattice feature that Allen talked about 2 days ago, due to the interlayer hopping term here, the interlayer hopping is also a complex number. And that will actually generate exactly a Haldane model in each valley in certain twist angle. And then when you take into account the other valley, then you get actually a K-Malay model with that these flat bands are actually Chern bands with a Chern number, a non-zero Chern number. And actually, in this case, would be Chern number equal to ±1. So that was the theory in 2019 and 2021. And immediately after that, actually many theorists realized that now you have flat Chern bands, you have strong interaction. This is a platform for interaction-driven Chern insulators, and maybe even fractional Chern insulators. Okay. And one thing I also want to mention is actually that the sublattice sites here, the wave function is actually living in two different layers in a sense. So you can actually, when you apply a vertical electric field through the bilayer, the Stark shift is actually the same as the interlayer potential difference. Well, the interlayer potential difference is the same as the sublattice potential difference in this case. So if you can apply an electric field to the system, you can also change the Chern bands from the bands from Chern bands to actually topologically trivial with a Chern number equal to 0. So by tuning the electric field, you can also change the band structure of the system. So this is a typical Debye structure that we look at. Sometimes a bit more complicated, but this is sort of the idea. This is the twisted bilayer sample sandwiched between boron nitride, which is very good gate dielectrics. And then the top and the bottom are usually graphite gates, pure layer graphite gates. And so because we have two gates here, we can tune independently the density of electrons in the system, as well as the vertical displacement field through the bilayer. And because the vertical displacement field can also tune the topology of the bands, so this is a kind of phase diagram that you can try to remember. In the small electric field regime in this gray area, we are talking about the system is in the layer hybridized regime, so that the Chern number is non-zero for the bands. And if you apply a large enough electric field, you push all the electrons to one layer. It's called a layer polarized region, and in that case, the band are non-topological, so the Chern number is 0 there. So it looks something like this, and the gray area actually expands with density, just because electrostatics require that the more electrons you put in, the more electric field you need to polarize all the charge to one layer. Okay, and the convention for labeling is actually that nu equal to 1 is 1 electron per moiré unit cell, or you can think of it as a half-filled flat Chern band. So that's the convention that I'll be using. So, so this is the outline. I hope, let's see how far I can go. In the last year, there were actually several experiments talking about finding fractional Chern insulators in this particular system, twisted moly telluride, one family of this twisted TMD. And first from optical signatures and also thermodynamic measurements. And very soon after that, a few months later, also people directly demonstrate the measurement of RXY that is quantized to the expected value in zero magnetic field. And so I will be talking about our story here using thermodynamic measurement briefly, and then I will move on to the FTI work. And so the idea is the following, that we want to measure the chemical potential as a function of density or the filling factor. And that from there, we can actually extract the compressibility, the n d mu. And if it's 0, it's an incompressible state. If it's non-zero, it's a metallic state or compressible state. And for both the band insulator and the Chern insulators, it's an incompressible state, so this should be 0. However, the Chern insulator can actually gain or lose states under a magnetic field because of the edge states. So basically, the idea is that to measure how the Chern insulator gain or lose states under a magnetic field. And the formula that governs how that actually happens is called the Strader formula. And so this is the filling factor for the particular incompressible state. This is the magnetic flux divided by the magnetic flux quantum, and T and S are the quantum numbers, such that T is the number of electrons added to the sample per threaded magnetic flux quantum, and S is the number of electrons added to the sample per added moiré unit cell. And if it's a topological trivial state, so T is 0, so there is actually no dispersion of the state with magnetic field. For an integer Chern insulator, both T and S are integers. And for the fractional Chern insulator, both T and S are fractions. So that's sort of the idea. And we actually sort of, at the beginning, we did not, we're not able to make a very good context to the material. So we actually use a optical method to measure locally, the sort of the readout locally, the chemical potential of the system. Okay, so how it works is the following, that in addition to the sample, we actually put a sensor, which is actually separated from the sample by a thin layer of boron nitride. So the two are actually not touching to each other, but they are separated by a thin dielectric layer. And we can actually, in this kind of structure, we can think of that top gate and the sensor are acting as the top and the bottom gate to the sample. And the function of the bottom gate is to actually fix the sensor to a fixed reference point. Okay. And this is the work by these two people here. And the sample is the twisted multi-telluride here. And the sensor we pick is actually a monolayer tungsten selenide. And it has a band structure. This is the band structure of the sensor, which is a very trivial semiconductor. But naturally, you would like to pick the reference point is that you would like to fix the Fermi level of this sensor to touch just one of the band edges, either the conduction band edge or the valence band edge. Okay. And to read that out, you can actually look at the strength of this vertical transition that promote electron from the valence band to the conduction band, leaving a hole behind in the valence band. And once your Fermi energy actually just move to the valence band maximum, the strength of this transition actually shows like a broadened step function, because actually once you put the Fermi energy there, you introduce Pauli blocking for the optical transition. And as a result, this kind of step function will provide a very natural reference point. Yeah.
There's no exciton.
Huh?
There's no signature of exciton on objects.
Yeah, actually, this is really looking at the exciton. But also, when you have excitons, this Pauli blocking is not going to be complete. And in fact, the excitons will turn into charge exciton resonances. But the neutral exciton, actually, if you look at the particular photon energy, the neutral exciton is nearly gone after you just put some doping into the valence band. But there is exciton, yeah.
So this line is the intensity of exciton?
It's the integrated intensity of the neutral exciton. And once you dope it, that disappears. And because that turns into charge exciton.
This is absorptions rather than emissions.
This is actually reflection contrast. Yeah, it's a combination of real and imaginary part of the optical conductivity. Yeah, but the idea is actually that this sharp step function provides a reference point, and we just pick the reference point in the middle of this curve here. And so the advantage is actually that it's about it's a local thermodynamic readout with some micron resolution, and without going into fabricating complicated FETs, SETs, for instance. And then in our experiment, we basically change the top gate and the sensor gate voltage, these two voltages, in order to tune the filling factor and the electric field through the sample. And the bottom gate is to fix the sensor at that reference point. And we just use a feedback circuit for the optical readout and always try to lock the sensor at that reference point. And with this experiment, you can directly read out the chemical potential of the sample from the bias voltage that you apply between the sample and the sensor. and the backgate voltage that you apply in order to keep the sensor in the reference point. And this capacitance ratio is these two capacitors here that we can actually calibrate using the quantum oscillations in the sensor. Okay, so that's the idea, that reading out the chemical potential. So this is a map of the incompressibility, the mu dn, as a function of the electric field and filling factor of a particular sample calibrated to be 3.4 degree with a Moiré density of about 3 × 10⁻¹² per centimeter square. Okay, and you can sort of see that it looks like the electrostatic phase diagram that I asked you to remember. In the small electric field region, roughly enclosed by this dashed line here, it is the bands are topological. Once you go to high enough electric field, the bands are non-topological, as you will see. And then here on the right-hand side, I just make a few line cuts. The blue curve here is cutting exactly across the zero electric field where the bands are expected to be topological. And you see a few incompressible states, for instance, at filling 1, a very strong one at filling 1, one at 2/3, 1/3, and 1/4 filling factors. So there are fractional states. And once you apply the electric field into just exceed this region here, just into this region there, the -1 incompressible states survive, but the other states are gone, more or less. Okay, so those are the other curves here. And another measurement that we can do, because now we are just doing it locally, optically, to read out the chemical potential, we can also do another measurement, which is the magnetic circular dichroism, to see whether there is time reversal symmetry breaking at the same point on the device. And for instance, if we park at filling factor 1 here at small electric field, you see a nice magnetic hysteresis curve that shows that the system really breaks time reversal spontaneously. And if you park at 2/3 at this state here, you also see the nice magnetic hysteresis. So the states are certainly incompressible and they are also magnetic. And so the question is just that whether these states are Chern insulators or not. So to do that, we just go back to, we try to measure the strata formula. And this is the measurement. I'm plotting again the incompressibility in this case versus filling factor and magnetic field, not the electric field. We fix the electric field at 0 so that the bands are topological there. So this is the layer hybridized region. And now you can actually see that the filling factor for the -1 and the -2/3 state, they both disperse under a magnetic field. So that measurement shows that it is indeed, they are Chern insulators. And as a control experiment, you can actually apply a large electric field that the -1 state still survive. You can look at its dispersion under a magnetic field, and there's no dispersion under a magnetic field once you layer polarize the bands. And this is just a mod insulator that it does not have any non-trivial topology. So I don't want to get into the details, but we can actually use the quantum oscillations of the sensor to really calibrate each of the gate capacitance and calibrate the twist angle. And with that, we can actually determine the two quantum numbers in the strata formula, T and S. For the -1 state, the T is within error bar is equal to 1. And also the S is also equal to 1. For the 2/3 state within error bar, actually T is equal to 2/3. And the S is also equal to 2/3. So both just these measurements show that the 2/3 state is actually a fractional Chern insulator. Okay. And you can also do this kind of measurement on different twist angles from 2.7 degree to 3.8 degree. And basically, these states are pretty robust there. Both the 2/3 state and the filling 1 states, they keep to be Chern insulators and fractional Chern insulator with little variance in the angle. Yeah.
Yeah. So I guess that the probing area is about the diffraction limited area about the micron. How that sample is homogeneous that it uses change the location?
So if you ask me for a transport device that we make, because we pick only those that is uniform within about 5 micron by 2 micron area, it's pretty homogeneous in order to do the transport. In this kind of device, we did not try to pick those ones that have a large area homogeneity, because we can just measure locally and you can easily see angle variation. Not that much a problem for large angle device, because if you have say a certain delta theta in your angle error, in large twist angle, the angle error is not that huge a problem. But small twist angle device, you can easily see Some area is 3 degrees, some area is maybe 2.5 degree or
So
something.
when you do the capacitance study calibrations out of quantum oscillation, do you do that everything is local?
At that particular point, yeah. Everything is done at that particular point. Okay, so a final word before closing this topic is that you can also apply electric field to make the bands to be non-topological, and you can measure the charge gap of that incompressible state. This is the FCI state, the two-third filling, and you can actually see that once you apply the electric field, the gap goes to 0, so it goes to a compressible state. Looks like somewhat continuously, and also you lose the ferromagnetism. So this is a part of the Curie-Weiss temperature. Exactly at those critical point, the Curie-Weiss temperature is no longer positive, so you lose the ferromagnetism immediately. Okay, how much time do I have?
About altogether 15 minutes.
Okay, so
10 minutes for
10 minutes. I'll talk about this roughly. It's protected. So it's a FTI protected by SZ conservation. I'll convince you that's the case at least. So it turns out that we discussed with people like Liang Fu, and at some point you told us that the magic angle is around 2 degrees. So then we try to make a device down to 2 degrees. It turns out that it's actually pretty challenging because the system tried to relax to this ferroelectric structure and a very small twist angle. But the heroic efforts of this group of people here really realized this device. So this it's a device with a pretty complicated structure here. Let me walk you through a little bit. It's 2.1 degree device with a moiré density about 1.2 times 10 to the 12 per centimeter square. And it's calibrated from the Landau fan of this device. It's a dual gated device. So this is the top gate and the bottom gate. And this is a twisted bilayer sample. And we use platinum contacts to try to reduce the contact resistance. I will talk about that. And in addition to that, to improve the contact, we use a monolayer of tungsten selenide as a tunnel barrier that separates the sample and the contact. And on top of the top gate, we actually pattern another series of gates. One of them is actually the contact gate, the CG here, which is to turn on the contacts. I'll tell you a little bit. And then the other one is the split gate. It's basically to turn off those regions that you don't want in the channel. So this is a picture of the device. We actually have more like an H shape for the device. It has 4 contacts that work, and the rest of the device is actually disconnected unintentionally from this region that has uniform moiré region. What we usually find out is actually that for those who care a little bit about the details is that if you have a uniform moiré region that separates from the region with no moiré, typically it breaks, the channel just breaks there. Maybe it's just cracks or something that happens. But we have a 4-terminal device here. So this is actually the contact structure that I want to talk a little bit about. This contact gates actually heavily hold up the twisted moly-telluride in the region immediately adjacent to the platinum electrode. The heavy hole doping is to actually reduce the contact resistance between the metal and the semiconductor exactly in this region. And the channel is actually gated by the top and the bottom gate. It turns out that we can write down roughly the contact resistance in this kind of series in resistance circuit. And it turns out that the contact resistance is really dominated by this junction. This junction here, from heavily hole doping to variable doping in the channel, is quite transparent, actually, as you will see. And so the contact resistance actually is totally independent of the electric field and the filling factor inside the sample, because this is only changed by the local gates there. Okay. And this is the contact resistance that we measure as a function of the temperature. Even down to millikelvin temperature, we can get a contact resistance about 20 to 30 kilo ohm. This number may not be very impressive for people doing graphene, which typically you get 1 to 2 kilo ohm or 1 kilo ohm or something like that. But it's actually already pretty good. It's, I would say, very good already for the twisted TMD devices. And so this is a map of the longitudinal resistance.
How does the WSE2 help with contact?
We figured that if you don't put WSE2, you actually often you cannot turn on the contact. With the WSE2, you have a much better probability to turn on the contact.
So the platinum dopes the WSE2, which,
So WSE2 is undoped. The band alignment,
but,
it's never doped.
but you have the platinum and then you have the WSE2 and then you have
The WSE2 there is still an insulator, but the tunneling into
Oh,
that,
yeah.
it makes it a better contact actually. Yeah.
you,
I think the reason is actually that the energy gap of this 2D semiconductor is a function of doping, and also the also function of the dielectric constant of the environment. If you directly put the material on PT, you actually have two different band gaps across here, and that is actually a very large Schottky barrier. But if you put some layer in between, you reduce that amount, and that will actually make the contact better. But if you put too much, then you just get too much of tunnel barrier. Yeah, that's sort of our working hypothesis,
just
but there's no,
diminishes the field strength effectively, just misplacement.
yeah.
Yeah.
So this is a electric field and filling map of the longitudinal resistance. And you can actually see filling one state not very clearly, but actually, let me just show you the line cut at the zero electric field region. That's basically the region we are mostly interested in. Filling factor 1, you get 0 Rxx, but the quantized Rxy, that's the Chern insulator. And you can also see that there is actually a fractional Chern insulator around filling factor 3.5 with a weak Rxy plateau here, not very well quantized, but it is there. There is a Rxx dip. But for all the other states like filling factor 2, 3, 4, 6, you can actually see all the way up to about 8 or even more beyond that. It really just shows that there are many, many states in this device because it's a very small twist angle. All the bands are really, really flat. But you look at this, it's actually a bit strange that all the states, the 2, 3, 4, 6 states, they have nearly 0 Rxx, but also 0 Rxy. So because it has nearly 0 Hall response, this cannot be Chern insulator, not like a filling factor 1. So this cannot be chiral states. So what are these states? So what we try to measure, it's the FCI. Then what we do next is actually we measure a two-terminal resistance as a function of the filling factor. So this is the configuration. We short these two contact, we just measure the two-terminal resistance. And we calibrate the contact resistance at very high doping, and we just subtract off that one constant contact resistance. And the blue curve is the two-terminal resistance after that subtraction of a constant contact resistance. You can see this 1, 2, 3, 4, 6 states, and the one has a quantized Rxy, but all the other states have 0 Rxy, nearly 0 Rxy. And this is a plot of the two-terminal conductance, is 1 over the two-terminal resistance. As a function of filling factor at different electric field, you can actually see that some clear steps of 1, 2, 3, 4, 6 in units of E squared over H. Okay. And I want to note that for the incompressible region, the conductance is actually independent of the electric field. But for the compressible region in between, you can actually see that the two-terminal conductance is dependent on the electric field that we apply to the sample. So the 2, 3, 4, 6 states cannot be chiral states because of the vanishing Hall response. And you actually, with this geometry, the filling factor 3 states is very special because each edge actually contributes a 3/2 conductance quantum resistance. So it implies a fractionalization in this case. So we can do a little bit better, actually. Because we have 4 contacts, we can just do a series of non-local two-terminal measurements. And basically, this idea is really following the work by Andreev, Pablo, and also Ray in the 2014 paper. They were studying the quantum spin Hall effect in graphene under a high magnetic field. But the simple story is actually that every time you float an electrode there, thank you. Yeah, you can actually provide a point that can let the helical edge state to equilibrate at this region, so that you can actually use the Landau-Butikow formula. You can build up this effective circuit model for the measurement. For instance, here you have 2 edges in parallel, so you have 2 edge resistors in parallel. Here you flow this electrode, so you have 2 edge resistors in series here and 1 edge resistors here, so they are 1 and 2 in parallel. Here is actually 2 and 2 in series, and then they are in parallel each other. So this is then you can actually really predict that what value that you could measure using this circuit model. So let me just, long story short, this is a filling factor 2, the quantum spin Hall insulator, two-terminal conductance versus the electric field. And once you go beyond the critical electric field, the system just transitions into a topologically trivial state. So this, you don't need to look at there. You just look at the small electric field region. And each of this dashed line with the particular color is the expected value if your edge carries exactly one conductance quantum. And for instance, this contribution will give you a 2e squared over h. This will just measure effectively one edge conductance is 1e squared over h. So this measurement just confirmed that this is indeed a quantum spin Hall insulator with one conductance quantum per edge. You can do the same thing for filling factor 3. At zero electric field, again, you just need to look at the small electric field region. And the dashed line are the expected value, the solid line are the measurement value, and they agree reasonably well. And the conclusion is actually that each edge carries a 3/2 conductance quantum, just like what I told you about. Okay, so the only thing we can think of a state that with quantized two-terminal resistance and a zero Hall resistance is a quantum spin Hall insulator. So I think there should have some and also this measurement really supports that they are helical edge states. So yeah.
So why does it goes up? mu secant to 3 versus mu secant to 2, where the conductance goes down?
Meanwhile, this goes down.
Yeah.
Yeah, actually, this is transitioning to a trivial insulator, and this is transitioning to a metal. Yeah. So the two are different. Yeah. Okay, so just a few quick comments. The nucleus 2, 3, 4, 6 are actually single, double, and triple quantum spin Hall insulators. And you may wonder why you actually can have an even number of helical edge state pairs on the edges. And the reason is because of the SZ conservation. So this quantum spin Hall insulator is actually not protected by time reversal, but it's instead protected by a SZ conservation. And you can actually check that experimentally if you apply an in-plane magnetic field, and that will actually destroy the SZ conservation. And a small in-plane magnetic field can actually suppress the edge conductance quite a bit. Okay, for all the incompressible states at integer fillings. But if you do the same thing for the compressible region, the in-plane magnetic field would not do anything. And filling factor 3 states, we think it's a fractional quantum spin Hall insulator. This is the band structure. It has a series of a C equal to +1 Chern band at the K value and a series of C equal to -1 at the K prime value. They are very flat, almost like Landau levels. So nu equal to 3 is actually corresponding to a half field, 2 Landau levels of the second flat band. Okay, so they pair. So possibly it's indicating some kind of composite fermion pairing. And I would just say that there are many existing theory at this point. Some say that you can break time reversal. Some say that you probably preserve time reversal. Some say that you can carry E/4 charge. Some say that you can carry E/2 charge. And it's all over the place. And hopefully there will be some important progress in the future that we would know the nature of the states. And finally, is the energy scale of the states. We can do temperature dependence. And the short message is actually that the nuclear 3 states disappear at a temperature about 3 Kelvin. So that's roughly the gap size of the state. So it's pretty small energy scale. And with this, I just put down the summary and happy to answer any question.
So for the last part, what is the reaction of the system out of field, out of plane field?
Oh, out of plane field actually does not do anything, almost.
Nothing. Wow.
Yeah, it's protected by SZ.
Yeah.
Right. So it actually, this is another thing that we really quite believe that this is true. Out of plane field, it doesn't do anything, but in plane field, it actually does something. Because for the TMD, usually you would expect the opposite. If it's bulk transport, many samples that we study, you apply in plane field, it does not do anything. Out of plane, all the effect comes from the outer plane field, right? Yeah, but it's opposite here.
Yeah, I have a question. So since it's
Louder a little bit.
if it's a quantum spin Hall effect, would you expect some MCDs signal in those samples at the edges, or have you seen any?
Yeah, actually, you would, because only if you drive a current. If you drive a current, you should get spin accumulation on the edges, and that in principle can be probed, but we have not been able to do it yet. Yeah.
Yes.
So if I remember correctly, Tritep and Yang's prediction from 2021 was maybe general for TMDs, and specifically they were looking at tungsten selenide, I think, at 1.4 degrees or something. Is there a specific reason you understand now why MOT2 should be the right choice rather than other?
For reasons we don't know, maybe I don't know, maybe Liang at some point can answer the question also. We do not find any FCI in twisted tungsten selenide. We do lots of transport studies on that sample also. You can find some other things, but it's just not the FCIs.
And it's possible to go down to low twist angle 1.4.
That's pretty challenging, yeah. So we've been looking at a larger twist angle in terms of the transport device, yeah. So that may actually be the reason, because the mass for the multi-telluride is heavier, so the bands are flatter at a given twist angle.
Is this compatible with building interferometers? I mean, can you?
I think it is possible. Well, it's an insulator, right? You can actually you do those quantum point contact here to get it off, but I think it's at the same time really challenging. The twisted samples are pretty hard to make. I think at this point we are not trying that kind of experiment. I think it's just too far away. I think we just need to develop how to make these devices more reliably first. Yeah.
You mentioned this TI is not preserved by time reversal symmetry, but by SC symmetry. Is that the reason why in your data of RXY, at those integer filling factors, there's a slope of RXY? So instead of RXY equal to 0 for finite range of.
Yeah, actually, there are certainly some features.
Only 0 at a single point.
There are certainly some features that we don't understand. I think you're talking about this slope here, right?
Yeah.
But it only happens at filling factor 3. For 4 and 6 and 2 is not the case. So filling factor 3 is like that.
Yeah, but you mentioned 3 is the FCI state.
It's the FTI state.
Yeah.
But the others are TI states,
right? And
they are also protected by SZ conservation.
Okay.
Yeah.
Okay, great. Thanks very much.
Okay, thank you.
Okay, next talk, Boris Spivak, Seattle, Debye relaxation in superconductors.
Change this a bit time.
It's
Yes.
you have to pay. You have to pay.
Yeah, sure. Sure.
Game right?
Oh. Sorry, I took the mic.
Yeah.
Oh, yeah. That's very important.
Yep.
For you, Boris. I don't want to get out of the picture.
To follow. Microphone.
Take this first of all.
Whatever you want. Now take this one.
No way.
Yep.
Нет, ты мне дальше все эту штучку.
Oh. Good question.
No, это
Yeah, I know.
But maybe there is a pointer here. It's okay. There is a stick here.
Use it as a point, right?
Okay, look, it doesn't really matter. So thank you for invitation, and Boris, congratulations. Boris is a very important person in my life. So he taught me a lot, and he also helped me a lot. I don't have time to give lecture about it, but I really owe him. This is my tutor. What did you do? It stop working.
Use it as a
Oh,
point.
okay.
This is my title, my name, place where I'm working. These are my collaborators. We did it with Anton and Andreev and the students. I'm going to speak today about two effects: microwave absorption in superconductors and IV characteristics of SNS junctions. And first question, why to speak in one talk about two effects? And answer is because they are described by one simple formula, just one simple formula. So if I will not have time to go to SNS junction, right, please believe me that I don't, second part of my talk, I'm not going to say anything new. The effect which I'm going to speak about is similar but not identical to the Debye relaxation mechanism in gases. And by the way, I learned what the Debye relaxation mechanism is very long ago from Boris in the context of coping conductivity. But anyway, to speak about relaxation, to begin with, I have to say couple of words about relaxation times. In superconductors, some metals, and in the metals there are at least two relaxation times, elastic and inelastic. And typically in films, for example, elastic relaxation time is much shorter than inelastic by many orders of magnitude. How many? I don't know, and I don't know who knows. It is very difficult to measure inelastic relaxation time in metals. You may think that weak localization gives you information about it, but weak localization measures shortest out of inelastic relaxation time. And in the Debye relaxation mechanism, it is longest. So the longest ratio, which I know in the literature, was from Mikhail, who measured how quickly metal cools. And according to him and Mikhail, this ratio could be 8, 9 orders of magnitude. And my goal, of course, not always. And there are several inelastic relaxation times. And my goal will be.
But what if you take, say, frequency-dependent relaxation time and associate frequency-dependent part with tau electron and independent part with tau inelastic?
So it's
if you consider, if you try to extract frequency-dependent relaxation time from the data.
From which data?
For the emission data.
So it's as a
from the scattering data. Okay,
Okay.
from optical conductivity data.
No. Optical conductivity is very high energy. So it's completely different story. We are speaking about low temperatures. Superconductor, 1 degree, 10 degrees. So it's 4 orders of magnitude up, right? So the question is in which data, right? Okay. So first, microwave absorption in metal is featureless. This is through the conductivity, density of states in normal metal, Fermi velocity, elastic relaxation time, and its frequency is much smaller than elastic relaxation, inverse elastic relaxation time. Through the conductivity controls. Absorption and inelastic relaxation time doesn't play any role. And also non-linearity is very small in absorption in metals. In superconductors, there was also kind of history of this. So in superconductors, this is supercurrent density, superfluid density, superfluid momentum. This is conductivity, this is electric field. And this conductivity is controls absorption, microwave absorption. This is subject of many important people worked on it, starting with Bardin, Schrieffer, then Larkin, Ovchinnikov, many others. This is kind of result at small frequencies, smaller than omega. Don't pay much of attention to this log. This formula is done when gap is isotropic. When it's anisotropic, it is cut off. But anyway, density of singularity of the density of states is broadened anyway. So this log may be factor 3. The message here is this, that if you measure microwave absorption in S-wave superconductors, it is always smaller or of the order of normal metal. Near TC, quasi-particles roughly like in normal metal. If you go down in temperature, microwave absorption decreases. And also, this is through the conductivity, so microwave absorption is controlled again by elastic relaxation rate. And our with Anton goal is to go one effect by another in superconductor and substitute elastic relaxation time for an inelastic, which means many orders of magnitude. And it goes with the price. And I will tell you what the price is. But first, the mechanism. So in the presence of electric field, superfluid momentum changes in time. As a result, density of state changes in time. And if density of state changes in time, it means that energy levels move in energy space. And in adiabatic approximation, and when it is valid, when it's not, when it is not, we can discuss. But in adiabatic approximation, quasi-particles travel with levels. As a result, non-equilibrium relaxation is created. Its relaxation is related to inelastic processes. It's, as a result, all effects will be proportional to inelastic relaxation time. It goes with a price. If you want to do it in linear regime, then density of states should be changing with electric field, for example, of superfluid momentum. But density of states is a scalar, so you need another vector. So, and I will speak about this later. This is kind of pedestrian demonstration. Effect is general, but we can speak about limit of pure superconductor where Boltzmann kinetic equation is applied. This is the distribution function of quasi-particles. This is conventional Boltzmann equation. Think about no relaxation. So you drop scattering integral. Think about uniform case. Then you drop these two terms, and you have derivative of time of n of p is constant, which means that distribution function labeled by momentum is constant, doesn't change in time. But energy changes in time because superfluid momentum changes in time. So as a result, this is how story starts. But I would like to be much more general. Why? I will tell you in a second. So you can think about levels like particles moving in one-dimensional space, in energy space, and then when density of states changes in time, there is a conservation law. Total number of levels is conserved. So this is continuity equation for levels. This is density of the level. This is velocity of the level of levels in energy space. So I can solve this equation, and this is velocity as a function of electric field. How electric field enters here, Ps dot equal to electric field. And I will call it sensitivity. This is a parameter which can be expressed in terms of derivative of density of states over superfluid momentum. Then there is another conservation law in absence of inelastic scattering. This is total, this is density of electrons, this is the occupation number of electrons. This is continuity equation also for total number of quasi-particles in energy space. And then if I add here inelastic term responsible for inelastic relaxation. I have both form of Boltzmann kinetic equation, which I personally never saw. This term is responsible for motion. Scientific term for this is spectral flow. It's when level moves together with electrons. And I will speak about mostly about situation when scattering integral can be written in relaxation time approximation. I can do it more. I can be more sophisticated than this, but doesn't really matter. Then I linearize this equation. If I'm interested in linear interacting field response, I linearize this equation. This is delta n, proportional to electric field. This V is sensitivity, which I mentioned. Substitute this expression into expression for entropy production rate. Yes.
Something to retain. So you're talking about thermally excited quasi-particles?
No, they're not thermally excited. They already exist. They just move. So there is a thermal distribution.
But you need thermal distribution. Can I put temperature to be 0? No quasi-particles, nothing.
Can you wait?
No.
No?
No, I mean,
Okay. Let me. Yes, you can. Your effect, amplitude of effect will be the same, but frequency interval where this effect will be not 0 will shrink to 0 as your temperature goes to 0. That's my answer. Okay.
But this is kinetic equation for quasi-particle.
For quasi-particle. Look, I'm giving you an answer. If you want me to explain how it works,
yes.
I give you hint. If not, sorry. The relaxation mechanism is proportional to longest of relaxation times. If you go to small temperatures, recombination time exponentially increases and concentration exponentially decreases. As a result, this exponent will cancel. But frequency interval where it happens will be exponentially small. That's what my answer. Okay.
Probably we should think about finite temperature for now, right? Right. The effect doesn't exist at 0. Yeah. Forget about 0. Think about finite.
Well, okay. Okay. Thank you. Anyway, look, answer question was, does it die as temperature decreases? Okay. Anyway, this is Debye conductivity. So I equate entropy production rate with sigma times electric field squared. And this is my formula. So you don't have to know anything else about this. So I divided it by drew the conductivity just to make it dimensionless. And this is a ratio between elastic and inelastic relaxation time. As I said, I don't know how many orders of magnitude. It decays when frequency is larger than an elastic, omega tau is larger than 1. It's similar to the relaxation mechanism. What's not similar is that it's constant, that frequency goes to 0, whereas the relaxation mechanism is quadratic and non. So that's the difference between superconductors. This is first place, it's new formula. It is correct for any superconductors, S, P, D, arbitrary disorder. So mean free path could be larger or smaller than mean free path. It is mean field formula, but it can be generalized, I think, for quantum fluctuations. It hasn't been done, but I think the generalization is kind of simple. But anyway, this is the main message here. the ratio between elastic relaxation time. Now, from this formula, you see the following, that this derivative of density of states over superfluid momentum should be not zero. So in density of states is a scalar. It means that you need another vector. So either you have S-wave superconductors, then you have to pass a supercurrent. And this is the price which you have to pay for the. Of course, there are another trivial mechanisms which I mentioned, which are proportional to elastic relaxation time. Now, if it is, for example, P plus IP superconductor, then this is not zero even in the absence of external superfluid momentum. And the message here is the following, that if you have a superconductor, you measure microwave absorption, and you see the value of sigma significantly larger than its value in normal metal, it's a conventional superconductor. So it's almost smoking gun for new kind of criteria, not criteria, kind of new.
And if it's just simple D-wave superconductor?
If no, no.
So it's not simply conventional, it should be spectral conventional.
Depends what me. Anyway,
Okay.
Look, you know what I mean. You need a vector, right? Okay. Now the rest is okay. You have to calculate this dependence of density of states of superfluid momentum. Hundreds of people did it in different limits: dirty case, pure case, mesoscopic, not mesoscopic. But yes, it is a price. If you want to do it in the S-wave superconductor, you have to pass supercurrent. In my understanding is that it is possible, but most of experimentalists don't do it because of leads. They don't like leads to pass a current. But maybe I'm wrong. Yes.
So that this expression still depends on the directions of the
Of what?
The expression depends on the direction of the PS. Is that right?
Yes, it is also anisotropic with respect to electric field in supercurrent. If it's S-wave, you pass supercurrent like this, there will be electric field should be parallel, should be component of electric field parallel to supercurrent, yes.
If the superconductor parameter has some structures, say D or D plus ID, whatever things, then
sure. I mean, anyway,
fractions that basically our
then we answer is complicated. My answer is this effect will still exist, but actually Anton will speak about vortices. In vortices, you will see that it is still survive, though your argument is the same. So supercurrent is like that, but it derails me from my direction. My short answer is yes. Anyway, so give me density of states, simple as possible, just to see what the price is for this. Pure case, delta tau elastic, much larger than 1. Dependence of energy of superfluid momentum is trivial, very well known. You substituted, this is a formula. This is a ratio which I talked about. This ratio is roughly a ratio between current, supercurrent, and depairing supercurrent. This is many orders of magnitude. This is dirty case also. This is roughly how it looks. If you have one relaxation time, you have a huge value of ratio between sigma and Drude, and then it drops when frequency is of order of 1/tau inelastic. And then, of course, there is another contribution which is conventional, which everybody calculated before us, but it's a high frequency. Now, by the way, this is The mistake, it's much higher. Anyway. Oh, I'm sorry. This is the wrong slide. I don't know how it occurred there. If you have several relaxation times, say, for example, phonon and then electron, then first omega, when omega is larger than longest relaxation time, it will decay, it will plateau, decay, something like this. The only experiment which we found in this area is a experiment with a group called Berggren. This is not a sample. Actually, this is single photon detector. So this is aluminum, and so this sample is not prepared, especially to measure this effect. It's a single photon detector, but for some reasons they measured microwave absorption. In this, and they pass a current. This is a current, and you see increase of microwave absorption. So this quantity here is proportional to sigma. Now, the reason why personally I didn't analyze kind of this divide whether our theory agrees with this experiment is the following: that this is a single photon detector, and it is a device to measure single photon. And if you prepare wire, this wire of aluminum, one energy of one photon is not sufficient to suppress delta. So this single photon detector will not work. So you have to damage this aluminum. And first person who damaged this aluminum to the degree that single photon detector works was a Grisha Goldsman in Moscow long ago. And then everybody kind of followed this recipe, but this is kind of a not very well controlled sample. And that's the best experiment which we have. Why? My guess is, it's not a difficult experiment, I guess, but you need leads to pass a current. Or I know several unpublished results when people just measured microwave absorption, which was much larger than normal metal microwave absorption. So then they have
Red is old field, not your field.
What?
Red is old field.
What?
Red line.
Red line, yes. The point is this, that if you ignore this and you pass a current through superconductor, say near TC, nothing dramatical happens, number of quasi-particles is roughly the same, you will have no dramatic dependence of conductivity.
Just for the context.
Huh?
Just for the context. So in Josephson junction or Josephson arrays, people measure microwave Shapiro steps for ages. So should they see anything like that?
Look, it depends. It's a question of frequency, as you see, right? And I don't know, I have to think about frequency at which they're measuring. So I don't want to answer this question in either way. 15 minutes, okay.
Including questions.
Huh?
Including questions.
Okay. Now, if you don't want to pass a current, that's fine, but then measure nonlinear absorption. In nonlinear absorption, one power of electric field will create 2 PS bar, and in that, then the same story. So in previous formula, you have to substitute PS for nonlinear, for PS created by electric field. So the prediction is that through superconductors, nonlinear microwave absorption is giant, many orders of magnitude larger than what you expect. I don't know why people didn't measure it. You don't need leads. in this case. Probably it's psychology that if you think that everything is like a normal metal near TC, so you don't expect any nonlinearity. Anyway, so as I promised, by the way, this formula can be also generalized easily. So not only, so it's very general form. And in particular, if you have a Josephson junction or array of Josephson junction, that's a formula, but there are several relaxation times in this case. And then the question is what the frequency and what you're going to see, but there is nothing else. So, this brings me to my next topic is the resistance of SNS junction. And as I said, you shouldn't expect any new formulas here. The idea is the same. You have SNS junction, you apply voltage, density of states because of Andreev reflection, density of states in normal metal region depends on phase difference. Levels move, non-equilibrium distribution is created. We calculate entropy production, has a conductance or resistance, dissipative resistance. What I'm going to speak about is IV characteristics averaged over the period of Josephson oscillation. So it's pure dissipative. So this is device, superconductor, normal metal superconductor. This is Josephson relations, derivative of phase equals to 2 electron charge times voltage. This is anyway. The same formulas. It says it's zero-dimensional approximation when diffusion time across the normal metal is much shorter than period of oscillation. So I can introduce distribution function, which depends only on energy. And by the way, in previous discussion, I forgot to tell you that I assumed that that elastic relaxation rate is very short, and the distribution function depends only on energy. Here is the same, but it also doesn't depend on coordinate. So it's just a function of energy. The same formula, the same expression for sensitivity. I also can write conservation law of total number of levels in continuity equation. Have this expression substituted here. The difference between what I told you about in the SNS junction is the following: that in the SNS junction, actually, there are IV characteristic depends on external circuit. So it depends whether you fix voltage or current. But this is a very technical thing. And so I solve this equation. Instead of entropy production rate, I can calculate, I just can write expression for current. By the way, maybe I would like to make the following comment. It looks very simple, but it was not very simple for me. And when I was thinking about what the real effect is, it is the following: that when you, it's the same like with the Debye relaxation mechanism. It also looks very simple, but when you think about how current really flows, it is about correlation between events of emission and absorption of phonons and phase of electric field. The same is here, so you can rephrase this effect in the following ways: that can you get some dissipation from oscillating supercurrent? And the answer is yes, because the supercurrent value oscillates, but it depends on its amplitude depends on distribution function. Distribution function also oscillates. As a result, there is a component of supercurrent which is in phase with oscillation of electric field. It's the same as here. As a result, I would like just to give you a result. Don't want to go to this simple algebra. There is nothing fancy here. But this is a result for IV characteristics in a case when voltage is fixed on SNS junction. This blue region is new. This is old. Many people, how many I don't know, many people, important people calculated this. This is new. This characteristic peak has to do with, yes, this characteristic peak has to do with the same effect which we saw in microwave absorption, that there is 1 over omega tau inelastic squared in denominator. This is similar to the bi-relaxation mechanism. So formula is also for conductance at small voltages is also similar to what you saw before. This again general formula. It is general SNS junction, so you don't have to think about whether it's pure metal, dirty metal, what kind of metal would be quantum Hall effect, for example, instead of metal. Doesn't really matter. This is new formula. Interestingly, this maximum would be much larger than critical current. So maximum of current here is much larger than equilibrium critical current. I will comment on this in a second. Anyway, but practically my understanding is that it's possible, but experimenters don't like to apply voltage to Josephson junctions. They kind of pass a current. So, but it's clear already from here what is going to happen. So if you apply current, there is a, anyway, this is unstable branch. So,
the negative differential conductance region. So
what?
There's a negative differential conductance region.
Yes, but it's a fixed voltage, so it's stable. At fixed current, it would be unstable. That's what, sorry?
What is shown here?
Yes, yes, that's what, this is at fixed current. If it's fixed current, this is IV characteristics. And I would like to show to you this, to turn your attention to characteristic feature of it. Again, I am not 100% sure about statements which I would like to make, but my impression is that most of experimenters, maybe all of them, measure critical current wrongly. Not only in Josephson junctions, but in films in general. And the reason is this, so look here. This is the region which I'm speaking about. These voltages are very small. How small, I don't know, and I will comment on this later. But anyway, this is the difference between critical current and current where it jumps would be parametrically big. But you have to measure small IV characteristics at small voltages. How small, if you take literally this tau inelastic, it is a really small voltage. sometimes. It depends on time, on temperature, but also anyway. So there is a plateau here. This wiggle means that there is a big parameter here. So it looks like a plateau with which corresponds to very small voltage and then jump, and that's the result.
But again, parameters that make this region large is what? You probably said.
So if look, it depends. Theoretically, at temperature larger than Thouless energy, critical current is exponentially small, and this jump is not exponentially small. So theoretically, it could be even exponential, but of course, practically, it's not. Okay, now about this inelastic relaxation time, which I was speaking about. I think it makes sense for uniform superconductors. In the case of SNS junction, it's actually not.
Sure.
Yes.
No, I told you.
Yeah, sure.
Your approach is that.
Yeah, sure. Yes. It's actually not an elastic relaxation time. It's a time to escape from this region, and this is, probably. Yes, sure. Okay, it's enough.
5 minutes for questions.
Good, good. So, message here. You have to substitute an elastic relaxation time to real escape time. This has now been measured in superconductor, an SNS junction. You can escape to the surface, you can escape in a bulk. If there is in a bulk, there are subgaps, the subgap states. This is already Hoping conductivity of quasi-particles, which has now been studied in superconductors. And finally, okay, so the rest of the message is the following, that, okay, almost everything which you want to know about small voltages, IV characteristics, in SNS junction, and also in an array of them can be done this way. In particular, you can consider non-reciprocity of IV characteristics of SNS junction. Of course, there is the Ansager's theorem that conductance, linear conductance of H equals to conductance of minus H, but in nonlinear case, it is not the case. It was in metals, it was studied a lot in the semiconductors. But again, in metals, this amplitude of non-reciprocity is controlled by elastic relaxation time. As a result, it is usually small. And here, it is giant. It's proportional to inelastic relaxation time. And there is another kind of the whole story behind it. So these IV characteristics look like this, but anyway, I have to finish. And this is my conclusion. Thank you very much for your attention.
And questions? Yes.
So if you have a distribution of this elastic relaxation times, what would be the conductivity?
If you have just two.
No, you have like broad distribution.
Okay, you have to do this algebra, simple algebra. I could tell you what if you have two. You have a big conductivity, go down, plateau, goes down, plateau.
You
Now
get something flat, like mega independent.
No, it will be a mega dependent because you will switch off. If you have a hierarchy of relaxation time, you will sequentially switch off all of them. Eventually,
will be linear.
huh?
Will be linear.
No, it depends on distribution function, of course.
Okay, for constant
For constant what?
distribution function.
Yeah. Yes, for constant distribution functions. Yes, sure.
So the reason I'm asking is because, like in high TC, there is this residual conductivity subgap.
Look, I deliberately didn't speak about high TC. First place, it's high TC. Second place, not a single word is known in high TC about the relaxation rates. And but there is a feeling that this is, by the way, the reason why Gizmo-Landau in high TC works much better, because it's Planckian. Relaxation rate is very short there. And so how short? Probably it will go up when you go to small temperatures, but I don't know anything about relaxation.
So voltage bias the Josephson junction.
What?
The voltage bias the Josephson junction that you initially showed.
Which Johnson?
Voltage bias.
Voltage bias, yes.
Then there is an AC Josephson effect, and the junction can radiate the some radiation.
Yes,
is
sure.
That in the part of the theory?
Oh no. It's very small. Yes, it does radiate, but contribution to IV characteristics is very small.
How do we know that? I think
I know. Look, it's my short answer. Yes, I know.
I thought kind of that depends on kind of radiation conditions, right?
Yes, it depends on radiation condition, but typically this mismatch is very small to begin with. But second place, you cannot look. What I showed to you is many orders of magnitude. So
the voltage bias IV characteristics with the negative differential resistance is something that is seen if you voltage bias the junction. So maybe I missed something.
in SNS junction, I would be very much
familiar with SSS junction, but
what is
I
Yes.
like Diamond Bridge.
never saw it. Okay. I'm surprised.
How, I mean, then I didn't get the sense of the numbers. Like, is it something immeasurably small?
No, okay, let's speak about numbers then. Say if relaxation time in aluminum at 1 degree is 10 to power minus 8, 10 to power minus 9 second, right? 10 to so 1 volt is 10 to the power. Anyway, so it's converted in voltage. It will be pretty small voltage, but my point is this, that it's shorter than this.
There are no more questions. Thanks very much.
Questions here?
Anton Andreev, same university, giant microwave absorption in a pin vortex lattice. Yes, you can use this as an old-fashioned pointer.
Is the mic on? Oh, yeah, the mic is on. Okay, thank you. So first of all, I want to thank the organizers for the invitation. It's an honor for me to be at this workshop and celebrate Boris's birthday, his induction to the Academy of Science. I cannot claim to be one of Boris's students, but in a way, I feel like I am, maybe a grandson, because first through Boris Altshuler and then Boris Spivak, I feel like I've been fortunate to be exposed to this wonderful style of doing physics, where clarity of the qualitative understanding is emphasized over math. Okay, so thank you and happy birthday, Boris. Okay, so my talk will be in some sense a continuation of what Boris discussed, and I will consider the application of that physics to a non-homogeneous superconductor. So I will discuss microwave absorption in type 2 superconductors, where a film of a superconductor holds a Brikosov vortices. So this work is done, it's based on a bunch of papers that are written together with Boris Spivak, Misha Tigelman, and also our former and current students, Tony Liu, Mike Smith, and Boris Pashinsky. So throughout the talk, I will only discuss thin films of superconductors. So this is a cartoon. Let's say we have this abricosov lattice in a mixed state. And I want to start by reminding how the flux flow conductivity is traditionally understood in this case. So if you apply a transport current through this film, this current induces a Magnus force on the vortices. Eventually, they become depinned, and the system goes into the flux flow regime. And in the flux flow regime, the pinning force becomes irrelevant, and the Magnus force is balanced by the friction force on the vortices. And the velocity of vortices is proportional to the electric field. That's essentially the Josephson relation. It's this drift velocity with which all the magnetic field lines drift. And in the traditional theory, the resistivity is all due to the friction of the vortex pores, which behave as chunks of normal metals. And so let me start by kind of reviewing of how this theory goes to offset what I'm going to discuss. So this consideration of the flux flow conductivity was originated by Bardeen and Stephen, and then many other people did work on this. And in a nutshell, what you say is that the friction force is proportional to the velocity of the vortex core, and the friction coefficient eta is proportional to the normal state conductivity. And it reflects the fact that a core can be considered as a chunk of a normal metal. And then with this expression for the viscosity, you can equate Joule heat to the energy dissipation rate due to viscous friction. And then substituting the flux flow velocity, one gets this well-known result of Bardeen and Stephen for the flux flow conductivity. It's essentially the normal state conductivity times this ratio of Hg2 to H. And so what's important is that the flux flow conductivity in the Bardeen-Stephen theory is proportional to the short elastic relaxation time, and the long inelastic relaxation time does not enter at all. And so continuing this Boris' talk, I will discuss under what conditions the long inelastic relaxation time can appear in the conductivity of this type 2 superconductors in the mixed state. So just Boris already did the introduction, but maybe one way to understand or to illustrate how the inelastic relaxation time can appear in the presence of a condensate momentum is the following, that if you consider the clean case, then the energy of a quasi-particle acquires a correction proportional to PS. This correction depends on the normal state velocity of the electron, and also the contribution of the same quasi-particle to the current is also proportional to the same velocity, which tells you that the quasi-particle energy and its current become correlated, and therefore current relaxation it becomes intertwined with energy relaxation in the presence of the superfluid momentum. And in the vortex state, in the mixed state, superfluid momentum is naturally present due to vortices, so we may expect that inelastic relaxation time will appear in the conductivity. Okay, so let me start with the simplest. That's an illustration of Debye relaxation, how this actually occurs, because quasi-particle levels move in time with energy space, setting off inelastic relaxation processes. Boris already explained that, so let me skip it. And so I'm going to borrow on these results that Boris discussed, where we studied the Debye relaxation in uniform systems, where it can be expressed in terms of the dependence of the density of quasi-particle states on the superfluid momentum, and apply these results to this non-uniform system. So I just want to mention that maybe that we have microscopic results for both S-wave superconductors and D-wave superconductors for uniform systems. And I'm going to borrow on the results for S-wave, where all these kind of sensitivities and the dependence of the density of states on PS was okay. Okay, let me start with the simplest example of appearance of the Debye relaxation in the flux flow conductivity. Let me consider low temperature regime, T much smaller than delta, where the quasi-particles reside only inside the vortex pores. So then this vortex pore can be considered as a zero-dimensional system where the density of states is essentially the density of states of a normal metal. So the density of states per vortex is the normal state density of states times the volume of the core, which is psi squared times d, where d is the film thickness and psi is the coherence length. But so if your film is disordered, then the volume of the vortex core depends on the position of the vortex, because these film thickness may fluctuate from point to point, and also the coupling constant, diffusion coefficient can also vary, and this therefore the coherence length will also depend on position. And then as vortices migrate through the system, it will make the density of states in the core time dependent, and this will set off spectral flow and Debye relaxation. So then if you can apply our old results for uniform systems, because cores are essentially zero-dimensional. And we did this with Misha Fiegelman and Boris and Mike Smith. We assumed weak disorder, so that the variance of the density of states fluctuations is relatively small, and the disorder has long-range correlations where the correlation length exceeds the core size. Then you can obtain this ratio of the Debye conductivity to the Bardeen-Steven conductivity in the following form. There's this big ratio of inelastic to elastic relaxation time, and then a bunch of small parameters which describe the strength of disorder and correlation rates. Yes, please.
There's no microwave here. No.
Good. Sorry. Yes, microwave will be kind of the main story. It's kind of background. So I think generally both flux flow conductivity and linear microwave conductivity acquire this contribution. It's kind of a warm.
But what are you talking about? Is it just flux flow, or you apply microwave on top of it?
Okay, this is flux flow conductivity. It's large fields. The next part of the talk will be microwave.
So it's DC.
DC, but
and also non-linear, right?
Experiences all this.
No, I understand that.
Waves.
The experiment is DC.
DC conductivity, right? And non-linear, because you have to depend the vortices to go to the flux flow regime. Right, but now it kind of looks like linear conductivity, but as I said, it's really a non-linear regime. So this Debye contribution looks independent of the voltage only if the electric field is sufficiently small. So this formula implies that the time of traversal of the correlation radius of the disorder is longer than the inelastic time. And then you kind of get this result. And if the vortices start moving faster, then the inelastic relaxation becomes ineffective. And this nonlinear conductivity falls off as 1 over E squared. And you get, roughly speaking, as a function of this electric field, this kind of Lorentzian form. And the crossover field, where this dependence on the electric field disappears, depends on the correlation radius of disorder and the inelastic time. And this is what was done. This is done here. Similar in the physical mechanism of contribution also exists in the microwave conductivity.
Big microphone.
Yes.
Sorry. Is it better? Good.
Should be. Try.
Okay.
1, 2, 3.
1, 2, 3.
Yes.
Good enough. Okay. Okay. So if you consider the same low temperature regime at weak pinning, and you study microwave conductivity, the same physics plays a role there. There, just the vortices are displaced by the microwave field from equilibrium, and because of the inhomogeneity of the density of states, you get a similar contribution for the linear microwave conductivity. I don't want to speak about it, just mention that it's kind of very similar. And instead, what I will discuss is, in my view, a more interesting case of microwave conductivity at strong pinning. There, the mechanism of appearance of the Debye contribution is, I think, much more interesting. So let me just discuss the setup. So now I would consider a vortex lattice, which is strongly pinned and kind of deformed, irregular. And now we have these vortices. We apply an AC microwave field. This microwave field induces the Magnus force, which induces AC displacements of the vortices from the pinning positions. And the question is, what is the conductivity? And before discussing our results, I'll remind how it's traditionally understood, this microwave conductivity, within the Bardeen-Stevens picture. So the picture is that the origin of dissipation is still friction, because now the displacements of the vortex force causes friction. And what you really need to understand is understand the velocity of the vortices induced by the microwave radiation, and then substitute this velocity into the Bardeen-Stevens form. So even in the presence of pinning, the vortex velocity turns out to be proportional to the electric field, but it's not equal to the flux flow velocity. And so let me go through this, how to understand this. So now at low frequencies, the Magnus force is not balanced by the friction, but primarily by the pinning force. And therefore, we can say that the displacements of the vortices are proportional to the transport current, which induces the vortex, the Magnus force. Then if you take the time derivative of this relation, what you find is that the velocity of the vortex is proportional to the time derivative of the transport current, which itself is proportional to the electric field. So you still have the same result, that velocity is moved with velocity proportional to E, but the coefficient is different. And so to find this coefficient, you have to basically relate the time derivative of the transport current to the electric field. This is can be expressed in terms of the effective macroscopic superfluid density of the sample. And traditionally, the superfluid density is expressed in terms of the Campbell length. It's analogous, similar to the relationship between the superfluid density and the London length. Now, the macroscopic density of the sample depends on pinning, and is characterized by the Campbell length instead of the London length. And the ratio of the Campbell length to the London length depends on the spring constant, K, of the pinning, and depends also on the magnetic. And then in this analysis, what you find is that the velocity induced by the microwave field is the flux flow velocity reduced by this factor of the ratio of the London and Campbell length. Okay, and as a result, what you find is that the microwave conductivity in the Bardeen-Stevens mechanism, which we call sigma Bardeen-Stevens prime, its ratio to the flux flow conductivity is this factor, which depends on the pinning strength and the magnetic field. And again, the inelastic time does not appear when this happens. And so now let's, what I will try to discuss is how the inelastic time and the Debye mechanism appear in the Debye relaxation in the pin vortex lattice. So in the microwave absorption in the pin vortex lattice. Okay, so the contribution I'm going to discuss exists even at perfect pinning, where vortices are not displaced and this friction plays no role. And the dissipation here arises because the distribution of the superfluid momentum outside the cores is disturbed by the microwave field, and this causes spectral flow, non-equilibrium population of quasi-particles in energy, and this distribution relaxes either via diffusion of quasi-particles across long distances on the order of the in-vortex spacing, or by inelastic relaxation. And so pictorially, so what I will discuss is relatively high temperature regime, where temperature is of the order or greater than delta. Then the quasi-particles live not only inside the pores, but also everywhere in the sample. And also I will stick to the London regime, where the intervortex distance is greater than the core size. Then roughly speaking, the picture looks like this, that the order parameter is healed quickly from 0 to its bulk value over length scales of the order of the coherence length. But then the threshold of the quasi-particle gap, energy gap, is actually suppressed below delta because of the depairing caused by the currents. And so this is the kind of picture on the horizontal line of this density of states. This is the BCS peak, the orange dashed line. And due to depairing, the density of states is, the peak is broadened and the gap is lowered below this threshold. And the main contribution to dissipation will arise from quasi-particles that live outside the core and in this broadening region of yeah. Okay, so how do we quantitatively describe this dissipation mechanism? So here the evolution equation, the kinetic equation for these quasi-particles essentially represents the diffusion equation. So now I want to stick to dirty superconductors. Tau elastic delta is small. It's a diffusive regime. And then at length, at frequencies smaller than the elastic relaxation rate, the evolution of these quasi-particles is diffusive. The distribution over momenta randomizes quickly. And then locally, the distribution function depends only on the energy. And the evolution equation is the diffusion equation, but with two extra terms. One is the inelastic collision integral, which we treat in the relaxation time approximation. And the second important thing is this contribution of the spectral flow. So the diffusion is elastic, it conserves the energy, but then because of the spectral flow, quasi-particles can be deposited to a given energy from other energies. And so this is this term which will play the main role. And here, V sub nu is what we call level velocity. It has units of 1 over time. And it can be expressed in terms of the time derivative of the local integrated density of states here. So I want to comment on the generality of this approach. So we are in the dirty regime. You might ask how, what is the correspondence between this description and the Larkin-Ovchinnikov equations, which are more general and also apply to dirty superconductors. So in Larkin-Ovchinnikov equations, our function n is the analog of their function f of Larkin and Ovchinnikov, but they have another function f1, which describes branch imbalance. So it's important that in the situation where the spatial gradients are small, generation of branch imbalance by the electric field is also small. And at the same time, because the time reversal symmetry is broken, branch imbalance relaxes quickly by local elastic collisions, and it does not generate these long relaxation times. So this is therefore Larkin-Ovchinnikov equations actually reduce to this equation with one kind of proviso. What they do have this spectral flow term, and this coefficient here is expressed in terms of some spectral current, has more complicated form in terms of Green's functions, but you can show that for small gradients, their expression reduces to this very simple local dependence. So this is a rather general scheme which describes non-equilibrium superconductors at small spatial gradients. And then to find dissipation, you just have to add the expression for the entropy production rate. It arises from diffusion and from inelastic collisions. Okay, so then now let's apply this diffusion equation. Yes, please.
So time dependence again, what's the source of time dependence?
The source of time dependence is time dependence of the density of states. So basically it's an adiabatic picture where you have a local equilibrium situation where you compute these, basically retarded advanced Green's functions, the density of states for the quasi-particles. It evolves slowly with time. So therefore you have density of states as a function of energy and time simultaneously. Good. It evolves with time because so you have depairing, right? density of states is broadened near the boundary of the gap because of the equilibrium currents. Now you apply microwave radiation that induces condensate acceleration. So this flow outside the vortices is changing. So your superflow is sloshing with time because of the presence of the microwave radiation. And therefore, locally, right, this called sloshing of the density of states. But now quasi-particles being normal, they cannot slosh together with the condensate. What they feel is this time-dependent non-equilibrium density of states, and they have to redistribute themselves, but they lag.
With the microwave frequency.
With the microwave frequency.
Polarization.
Yeah, exactly. Okay. Okay, so basically all life will happen outside the cores in this weakly inhomogeneous region. So in this region, in the London regime, the gap itself is uniform, and therefore dependence of the density of states on time arises due to the condensate acceleration. And this is this sensitivity that Boris discussed earlier, which is a vector quantity. And so what's important is that all the properties that are relevant for the dissipation are occurring at the frequencies in this near the gap, near the broadening of the BCS peak. And the strength of pair breaking locally in space is described by this pair breaking parameter, diffusion coefficient times PS squared divided by delta. It's small. And everything we need, like the width of the broadening peak delta epsilon, are powers of this pair breaking parameter. Also, the height of the density of states at the peak is also scales with this pair breaking parameter, and so is the sensitivity. And the only new input we need in comparison to uniform systems is the diffusion coefficient for quasi-particles in this broadening region. It's not equal to the normal state diffusion coefficient, but also is affected by pair breaking. And then with these inputs, we can try to understand what's going on in superconductors. And what we need then is to understand how condensate acceleration depends on the coordinates in this state. So I want to be in the regime where the distance between the vortices is shorter than the Pearl length. Then the change in the magnetic field due to screening currents is irrelevant, and we can assume that the magnetic field is uniform, and therefore this superfluid velocity arises because of the transport current and because of the vorticity of each vortex. So then the condensate acceleration arises because vortices are displaced, and this is described by this sum. This is the acceleration caused by the vortex velocities, and also the uniform microwave field. Okay, so then to see what's going on, let's consider a single plaquette given vortex A, and I will isolate from this sum a contribution of this native vortex A. So this is what we call near field acceleration. It is inversely proportional to the square of the distance from the given vortex. But then the other vortices and also the uniform field create a far field contribution, which does not decay with the distance from the vortex core, is essentially uniform. And we can estimate this far field contribution to be just the average condensate acceleration in the sample. And it's given by the electric field times the ratio of these London to Campbell lengths. And so the main message is that the near field contribution, which is peaked near the core, if you plug this contribution into our formulas, you essentially recover Bardeen-Stevens result. And the far field contribution creates a new contribution to dissipation, and it dominates in the wide interval of parameters. So let me start with the 10 minutes, even seven. Okay, quickly, low frequency regime. So the key point is that quasi-particles are some quasi-particles with energy below the percolation threshold are trapped inside the given vortex plaquette. They cannot diffuse. And so at the lowest frequencies, the dissipation is dominated by these trapped quasi-particles. So then let me go to I will assume that the inelastic time is longer than the diffusion time across this vortex plaquette. And therefore, at lowest frequencies, diffusion stops, and the dissipation is dominated by the longest time scale. To get this inelastic contribution, we consider the zero mode of the diffusion equation, and then relaxation occurs via inelastic collisions only. And the generation of this zero mode is proportional to this averaged over the plaquette product of condensate acceleration by the vortex sensitivity. So this angular brackets denote spatial averaging at a given energy in the trapping region. And so you can see that if you put this far field contribution where this condensate acceleration is proportional to the electric field for a symmetric vortex, this average vanishes and you don't get inelastic relaxation. But in the presence of spinning, vortices are distorted, and so this term does not vanish, and you do get a contribution to the conductivity proportional to the inelastic relaxation time with these similar coefficients. But you have to integrate over all energies up to the percolation threshold of this term. And the statement is that once you plug in all these sensitivities and how they scale with the distance because of PS, it turns out that this integral is dominated by the quasi-particles that are farther away from the cores on length scales of order of the magnetic length, which is the intervortex spacing. And with this, what you find is that the contribution, ratio of this Debye conductivity to Bardeen-Stevens has this anisotropy parameter K, which is non-zero due to distortion. In general, it's a water 1 with strong pinning. And then there's magnetic field dependence, which is hidden inside these two factors. Well, this is complicated, but if you assume very strong pinning, if you estimate the pinning constant by saying that when you displace a vortex by a distance of order of the core radius, you change the energy of the core by essentially condensation energy, then you get a much simpler expression, dependence on H is a simple power law, and then factors. Okay, so then, but now as you increase the frequency, the inelastic contribution decays as 1 over omega squared. Eventually, the inelastic relaxation becomes ineffective, and then diffusive contribution takes over. Then to discuss this contribution, let's forget inelastic relaxation and discuss just the diffusion equation. Also, importantly, now the distortion of the vortex is not important. You have a dipole and a distortion of the density due to the electric field. It diffuses, and the characteristic time scale in this case is the tau d, the diffusion time of quasi-particles across the vortex at these energies near the percolation threshold. And it scales with the vortex distance as this weird power with 8/3 with the intervortex distance. Okay, then for frequencies below this essentially tauless energy for diffusion, you get this diffusive contribution to be frequency independent. And here's the expression. Again, the same ratio of London and Campbell lengths appears here. And you can ask, at what frequencies does this diffusive contribution become of the same order as the inelastic one? And this occurs at the frequency omega star, which is the geometric mean between the inelastic relaxation rate and the diffusion rate across the vortex core. And at higher frequencies above the diffusion rate, you get a decrease with frequency with this non-trivial exponent 5/4 arising again from this sensitivity. At strong pinning, where you estimate the spring constant as the loss of condensation energy, again, this ratio of Campbell length to London length can be expressed in terms of ratio of H over HC2. And then these expressions for the diffusive contribution simplify. And we see that as this strong thinning, this far field contribution exceeds the Bardeen-Steven contribution at as long as magnetic field is smaller than HC2. And then it decreases at higher frequencies. Okay, so let me just summarize. We discussed microwave absorption, which arises from processes caused by the spectral flow of quasi-particles and associated with long relaxation time, either inelastic relaxation or the diffusion time across the vortex plaquettes. And for the inelastic relaxation, you need vortex distortion. And also I want to comment that although I discussed high temperatures, the same inelastic contribution due to vortex distortion also occurs at low frequencies. And for the diffusive contribution, you don't need vortex deformation. Okay, thank you.
Thank you. Questions?
I have a short comment. Michael Debye measured inelastic relaxation far from the vortex core by trapping quasi-particles in his qubits with huge precision. He saw that one vortex traps so many quasi-particles, two vortices trap twice as much quasi-particles, and it's sort of measured very, very precisely.
Okay.
Trapping strength of a single vortex.
It's like you should see these localized quasi-particles by impurities in the presence of vortex flow.
No.
Oh.
So quasi-particles diffuse,
diffuse,
and then they sort of see the vortex, then can sink
They sink into, okay.
down.
Okay.
This happens with a rate which is precisely I think it is precisely an elastic rate which you need.
Okay, great. I'd like to just learn more. Thanks.
Okay. More questions? No, thanks very much. Wait for 30 seconds.
Stay where you are. Stay where you are, yes. Don't move.
Any FBI conference, actual organization is done by Megan and Alicia.
What was done wrong with us, but everything what was correct, me. All the good things is made in the Alicia. And I think Boris wanted to say stuff.
Right, yeah, because people are leaving, so let me use this. But this particular break to say again how grateful I am to all of you who took this effort and came here first and delivered fantastic talks. Yeah, I would say every talk is just excellent, and I enjoyed every moment of this talk. And you told you mentioned so many my good qualities that I never expected that something like this can happen. But anyway, thank you again for coming here, for giving these talks, for discussing physics, and that's the greatest gift you could deliver to me. Particularly, I'm grateful to people who crossed ocean for that. Klaus and Sergei Baranovsky. Yes, he's still here, I know. So thank you. Thank you very much.
We still have two more talks. And we have now a coffee break, 25 minutes, so we reconvene exactly at 11.
And also, of course, I'm grateful, and most of all, probably to Alex and Brian Skinner, who organized this workshop, in spite of myself trying to avoid it. Yeah, and now I see I was wrong, but they were right.
Okay, so let's do this. Let's wait your hair, right? This one.
I could, might have to use like.
Yeah. So I need to talk to you. So immediately after.
Theater class. I know, no, wait, 2 more classes. I see you some other time.
If we do voltage biasing, you just see negative resistance noise. If you do current biasing, you see I'm always thinking about
Very sharp transitions?
Very sharp.
So that's
Like almost like a stab. And then once you go to that, will spin polarized.
Why spin polarized? I think SG is a considered
number comes to be a microvolt, I think.
I mean,
Sorry, I'm talking about out of plane.
out of plane.
Eventually, you will polarize all the states to one value.
Right. So then it will get the sharp transitions. You see that?
Yeah. Yeah.
Could be better than this.
It's actually in the
Depends on the rotation.
The band becomes much less flat, much more dispersive, and then you just see the levels immediately.
But it's a kind of even before you just kind of get into the value transitions. I just wonder there is some sort of kind of lambda level physics kind of sets in as somehow.
But the bands are very flat that we don't really see any fast.
Yeah. But I think let's kind of get back to the fractional Chern insulation. Eventually, this fractional Chern insulator is kind of you connect it to the fractional quantum Hall, right?
Yeah.
So I just wonder whether there are similar things I should expect into these cases. If there is any, say, kind of composite fermion picture is really kind of get there, right? And something like the 5F state type of things, maybe kind of the even denominator state is connected with this fractional Chern insulators. And I just kind of ponder it. So even before you get into the so for example, that when you turn on the magnetic field, do you see that the say gap is increasing?
Actually, the two stage strangely, gap is not increasing so much
At all. Or maybe
just
that
a little bit. Yeah.
little bit. Okay, so that's
It's,
so
it's
or
not changing much in the small. But
or at least that try to stabilize this
we don't see very it's a very clear effect on that.
Okay. How about this just this fractional Chern fractional
TI?
No, I think the spin Hall is what is the right way to call it?
Oh yeah, the quantum spin Hall.
Yeah, quantum
fractional
quantum spin.
Yeah.
That's what you call the fractional TI.
Okay, we want to use the term of fractional quantum spin Hall, but I think people just equate them.
Anyways, there is nothing said the magnetic field will not out of plane the magnetic field
It will
not
be
stabilize that.
pretty robust up to a few Tesla.
Yeah. And
But then it starts to get weird. Then eventually around 7 or 8 Tesla, it just suddenly transitions to
the value
states. Yeah.
Man, that's amazing. I think so that's
Well, hopefully
that's
more things.
Well, finally, you know that up to the fractional Chern insulation. Okay, so we've been seeing from the lambda level. This is
but this is I wouldn't say that is dramatically different, right? It's 2 time reversal. Okay, there's one very possible one. It's just 2 time reversal copies of that, especially against the SZ console.
But still, I think that has not been seen Or maybe you can say that, well, some of this even denominator state maybe, but yeah, I don't know. That looks kind of something not experiment.
Yeah, I think it's probably maybe 2 time universal copies of that.
Yeah.
Discussion.
Yeah.
Yeah.
Yeah. Right, so yeah.
Related to the Landau fence. So you mentioned the straddle. So it's
Yeah.
And
Yeah.
So for fractional chooses it's always the S or the new.
That's so far everybody found.
Yes,
at this point.
so,
Yeah.
so actually the straddle formula couldn't exclude the possibility that it's S and U is different.
Yes. Yes.
So-
You mean the S and T, right?
Oh, S and T.
Yeah.
sorry,
Yeah.
S and T.
Yeah.
So
Yeah.
basically it's very different. So I know, so far no one has.
Actually,
observed-
I think the straddle formula is strictly speaking is only proof for the integer case.
Oh,
I think that the fractional case, it's
Oh, so-
phenomenologically, it's always like this.
I mean,
It's probably not proved.
mm,
The straddle formula.
But for, I think, okay, I didn't, okay, anyway, so.
It's assumed to be, same. Right?
Integers.
It's assumed to also carry over the fractional states.
Yes.
Yeah,
yes.
we have never found anything that, the T and S are different. Other people did not see anything that is different. The T and S are different.
But I remember, for example, in some experiments that you predict the magnetic field to go to the quantum limit. So with an S is.
Oh, I think you're talking about like Andreev Young's experiment,
So,
the graphene with the lattice, basically a fractional field offset the band.
Yes. So-
That I think they found T and S
Different.
can be different.
So for example, S is 1/2, T is 1 or 2 is an integer, so that is, I think, very quiet.
Yes, yeah, those, actually, there are also these fractional states in the TMDs, but with the integer Chern.
Yes.
Yeah, with the integer, T. Then those are depending on what people call, sometimes it's called the symmetry breaking Chern insulator or, the topological density wave. It's
But
most likely just a Chern insulator with some charge density
fractional,
wave, right?
yes. So, and there's another, because I'm a little bit confused with all this terminology. There's another.
Yeah.
That is basically, I mean.
There is a Chern insulator with spontaneously
Iterations.
symmetry breaking translations.
Yeah, so, well, it's actually, it's basically actually in the team. And it could also be a fraction.
They can be fractionalized.
For example, also
1/3, 2/3.
2/3, I mean, but they can be different.
I think so. In principle, they can be different. Some there's no reason that they have to be the same.
But if they are different, that's not the fraction.
So I think as long as T is a fraction, it's
The fractional translation has to satisfy the S T because it's the solution of the charge. What you observed, the slope of the Landau fan should be the same as the feeling.
This part I'm actually not so sure. So S means that if you add a unit cell to your sample, it's what fraction of charge you add in.
Yes.
But T has a different meaning, right? It's just every magnetic flux quantum you add, how many charges you add.
But the fractional Coulomb effect, so the sigma xy is always equal to like,
T.
yeah, T.
Yeah.
So the T and it equals to what the fractional field. Thinking fractional Coulomb of the things as structure.
I mean, in fractional quantum Hall, there's no lattice, so.
Oh, yeah,
it's
yeah, yeah.
S.
There's no, there's no,
Yeah, so there's
it's
only
always
T,
zero.
yeah, so the S is really coming from the lattice. So it consists of the lattice. I think what drives the state would be like a fractional quantum Hall, gives rise to a sigma xy that is fractionally quantized, it's just a T, not the S. So, yeah.
But basically, it has to be in.
I think S does not have to be necessarily the same as T.
But everybody is.
So far, yeah, but I think. I've heard theoretically, it is possible that S equal to 1 integer filling state. But the slope can be fraction. Theoretically,
Oh, theoretically.
Yeah,
So
yeah.
what?
Some kind of a fractional excitonic insulator.
Oh, excitonic.
Yeah.
Okay.
Yeah.
Okay,
Then you can get a slope on the strata that is not 1. That is a fraction. Yeah. But I mean, phenomenologically, if you do the same kind of thermodynamic measurements, you can get the state that originally from filling 1, but with the fractional slope. Yeah. But it's theoretical, that is allowed.
Yeah. So for acoustic and multi-two, at larger sample, for example, so is there any interesting phenomenon you add in? Because you talk about the small.
So the tool is still quantum spin Hall. So at any quantum spin Hall, you add an in-plane magnetic field, you tend to suppress the edge conduction.
I see, but for lower, smaller.
Oh, no, then we never find any. The only place that we find an in-plane magnetic field dependence is quantum spin Hall. Because anything that is bulk conduction or involving a chiral edge state, there's no in-plane magnetic field dependence. Why so far? Yeah, because the spins are just locked like this by a huge, you know, yeah, you can see the version locked by a huge spin-orbit field. Yeah. So it's the only exception is really just so far as in the quantum spin Hall. Then the edge is protected by SZ or even the field breaks that, and it causes scattering on the edge state that we suppress the edge conduction. That's the only place that we enter. So how we find. Yeah. Oh, unless you, of course, you go to gamma.
Gamma.
Yeah, because in some DMDs, when put the multi-layers together,
yes,
you can actually get the gamma point to be above energy. The K electron.
Yeah.
Then the gamma, you actually have very weak spin orbit there.
Oh.
Then the influence magnetic field can do a lot above.
Oh, I see. It's the gamma value.
Yeah, that's gamma value. Yeah. These are the two exceptions, either quantum spin or gamma value.
I see.
Yeah.
Okay. Thank you.
Yeah.
他当时就问一下，是他说你们这些做理论的，对啊，然后你们这些做理论的知不知道怎么？然后他自己不懂为什么会会。
我忘了是哪，但是他们看到那几个小 famous 的 feeling，他们叫 FCI，他们说话还是可能好像他好像是有提到过一个什么，哎，是吧？他们
好几个不一样。其实 transport 和 RXY 都是。
哦，他们是说这种他们测出来的，
有一个说能不能把字动一下？
不一样，
是吧？
就是
对啊，也不是 optical，他说是 straight
大脑是在
就他看那个
Oscillation
RXX 的 peak，
对
XX 的 peak 跟那个加了 magnitude 怎么移，就在那个 magnitude 和那个feeling 那个 phase diagram，我就看 RXX 那个 peak，在这个长期里面
给自己讲笑话。
那个 peak 就 RXX 的 peak 就告诉你那个 gap 的位置在哪里。
然后你说那个 slope，
那个 slope 跟对那个 slope 跟那个 x y 不一样。
这个不是一个
对，他不懂为什么。
现象背后的
我可以假是吧？
不是你肯定不能是假是吗？
对啊，刚才他说
就是别人给你讲笑话，
但是这个大风刚讲，
阿米尔遥控比那里就一堆不一样，
但是加
跟他加了磁场。但是测这个就是要加磁场，只是说你到0的时候，
对啊，他能听到1.0的，
你说
能
哦，它就是在上面。
是啊，要是能的话，他发现了这个，然后后面的人就不会用这个磁场。
回想到这个
高磁场在高
会笑
啊，
对，这是一个有意思高磁场。
没有，我觉得他们如果把磁场继续加大的话，那条线会一直上去。
他们
这个太
就现在这些是。
你说它会连续的，
对啊，
会延伸到
但这个是一个思考，
是一样的，只是看那个在地磁场这个 stage 这个。
cycle 这个东西挺有意思。别问的话，这个
就他们阿米尔遥控比在测 major angle TBG 的时候，
然后我们这个
应该是没有 spontaneous 的 signature break， 一定要加磁场加足够大才 break 掉。所以他们的 FCI 是在比较高的磁场点看，现在只是说它有 spontaneous 的 signature breaking， 所以在很低的磁场，甚至等于0的时候，
比如说我
也可以看到。然后你画那个 strata formula 的 phase diagram 的时候，它就一直都有，像阿米尔遥控那里有缺了一块。
我有个
物理层面，你就是我的意思，你可以把它抽象成一个物理模型。后面这个 model 是
变质理方式 fraction， 那个1已经变成
这个更接近于这个能到3个现在的一个不过的是
这里的 square 跟那个 fractional charge 没有关系。就算因为它是 edge channel 导致的那个 conduction， 只要有一个 channel， 它就贡献一个 e square 的感觉。Mike Modify 是测，那里有2个 edge state 在做 interference， 就那个 interference，
所以一个
two fifths 的时候，它们是。不能往这里去。 如果完全它这个X、Y 是可以实现的，它是可以这样比例。那个 gap 啊，
它的觉得作用很慢，找到时候来。
看到这样子。
这个问题，
Your camera. Okay, camera.
Camera.
I suspect that.
Yes, let's see.
You sure?
Yeah.
Do you see us? Hello.
Oh, is
Yeah,
responding?
hello.
We can hear you.
Okay, and I can hear you as well.
Sound, check sound. Check out.
Yeah, I can hear you. Do you hear me?
Yes, now we can hear you. Everything is fine. Can you see us?
No, actually, I see the screen and I see myself. I think that the camera looks on the screen.
Oh, camera will go to the screen.
Oh, but
No, you.
Okay,
this is
okay, anyways.
Yeah. Okay, then give us a couple of minutes and then.
Yeah.
But
It's firstly seen essentially plasma oscillations in junction from inductance and capacitance.
Okay. I don't have a morning session, two talks on Zoom. The first one is Michael Glazov from Ioffe Institute, long range exchange interaction in Excitons from optics to transport. Yeah.
Okay, thank you very much. And first of all, it's a great pleasure for me to participate in this conference, and it's a great honor for me as well. Indeed, I'm going to speak about long-range interaction, long-range exchange interaction in that case. And this work has been done together with two of my students, Zahar Yakovlev and Alexander Shensov. So let me start by paying a tribute to Boris. And we have seen already these figures and this formula many times at our workshop, and we discussed a lot the Coulomb gap at the meeting. But for me, it is very important, a very simple interpretation of the effect, which was proposed by Efros and Shklovsky back in the days. Then they were speaking about importance of Coulomb interaction and actually the excitonic effect that determines the spectrum of disordered systems. So in my talk, I'm going to discuss normal, more conventional excitons. Then you have electron and hole in relatively clean semiconductor. So I will be speaking about their fine structure, about energy spectrum fine structure produced by the long-range exchange interaction, and about exciton transport in the presence of disorder. So the plan of my talk is shown here. And let me start actually with a very brief introduction to the systems and materials I'm going to talk about. So in this audience, I do not have to repeat and reiterate a lot about physics of excitons. So if you consider an insulator or a semiconductor and promote an electron from the valence band to the conduction band, then the imbalance of Coulomb interaction appears exactly as it was described in Shklovsky-Efros book and paper. And then you have an attraction between the
a positively charged hole and negatively charged electron. And then a bound state akin to a hydrogen atom is formed, and this bound state can, in principle, freely propagate in the crystal. And depending on the material and depending on the conditions, actually excitons can be very different. Their binding energies can range from units to hundreds of milli-electron volts. Correspondingly, their effective Bohr radius, the effective sizes, can be in the range of hundreds angstroms to tens of angstroms, again, depending on the materials. And in some cases, like in cuprous oxide, you can highly excite excitons. You can promote them to the states with large principal quantum numbers, so that these excitons becomes really big objects with the diameters typically on a micrometer scale. And actually, right now, it is quite clear that excitons, these Coulomb-bound electron-hole pairs, govern optical properties in many semiconductors and semiconductor low-dimensional structures. So the excitons were predicted almost 100 years ago by Jakob Frenkel, and there was an interesting coincidence that actually this prediction has been done while he was visiting the University of Minnesota, which also provides a link between what I'm talking about and the topic of our workshop. So let us move on. I'm going to speak about two-dimensional crystals, particularly about two-dimensional transition metal dichalcogenides. And we already had several talks about these fantastic systems, the very interesting optical and transport properties. And thanks to Kin-Fi, I do not need to repeat a lot, and I do not need to say a lot of words about spin-Weyl locking in these materials. So I just want to remind you that direct band gaps are formed at 2 points, K plus and K minus, at the edges of two-dimensional hexagonal Brillouin zone. And because of low symmetry of these materials, the threefold rotation axis, and lack of an inversion center, the optical transitions are chiral in a sense that light of a given helicity induces transition only at a given value. Say sigma plus polarized light, right-handed light, induces transition only in the vicinity of the K plus point of the Brillouin zone, so here, while sigma minus polarized light induces the transitions in the vicinity of K minus point. And this will be important for the fine structure of excitons and for the following. So I will not go into much detail on how these materials are particularly attractive and interesting. Let me say a few words about how the excitons formed, and I will start with a very simple actually situation. You have two-band model, the valence band, the conduction band, and then we promote an electron from the valence band to the conduction band. And in this simplest possible two-band approximation, we can present the wave function of exciton as a product of two-particle Bloch function, or two-particle Bloch amplitude, the periodic function with the period of the lattice, and some coefficients. So these two-particle Bloch functions correspond to the situation then a given state in the conduction band is filled, and actually one state in the valence band is empty. And usually one associates holes with time reversal counterpart of unoccupied states. In this way, it is natural to introduce the momentum and spin conservation laws. So if you use this approximation, and if furthermore you consider the Bloch amplitudes only in the vicinity of this band extrema, then you can transform this problem back to the very simple effective mass problem for the wave function of exciton, which is now in real space is presented as a product of the two-particle Bloch function. So this function really knows from which bands the excitons are formed, and this function is extremely important for optical properties, for selection rules, and also for the fine structure. And then there is a smooth envelope, which in its turn for ideal system is presented as a product of the plane wave corresponding to the translational motion of the center of mass and the relative motion envelope function. And the envelope function in its turn, it's textbook physics, it obeys the Schrödinger equation, very much similar to the hydrogen atom. And the properties of the crystal come into two parameters here. So the first parameter is the reduced electron hole mass, mu, and it depends on the system. So for transition metal dichalcogenides, this mu is about a quarter of free electron mass. So we're just somewhat lighter than the free electron here. And V is the interaction potential. And in fact, in transition metal dichalcogenide based systems, this potential can differ from simple Coulomb interaction for the following reason. So typically, the structures people study consist of a two-dimensional semiconductor, and it is encapsulated, say, in hexagonal boron nitride. And then if electron and hole are relatively far apart here, then of course electric field permeates the surroundings, and what we have is just the Coulomb potential at large distances, which is screened by the environmental dielectric constant. However, if electron and hole goes relatively close to each other, then the field becomes concentrated in this very narrow layer. Effectively, this is because of high polarizability of these two-dimensional materials, and then electrodynamics becomes essentially two-dimensional. In that case, the potential of interaction has this logarithmic form for small distances. And it turns out, particularly for transition metal dichalcogenides, that the effective crossover distance, this parameter R0, is on the order of several tenths of angstroms, and it is on the same order as the Bohr radius. So the effective potential can be nicely described by so-called Ritova-Keldysh model, which was proposed a long time ago, actually, for thin films of semiconductors, but it works reasonably well for transition metal dichalcogenides. And then depending on the surroundings, depending on the particular material, you can have excitons with rather large binding energies, hundreds of milli-electron volts, rather small Bohr radii. Still, these are large radius excitons in comparison with the lattice side. They cover at least several tenths, up to 100 of unit cells. And relatively short radiative lifetime, relatively strong coupling to the light, again, because the Coulomb interaction is rather strong. So I will not go into any details about interesting physics related to the excitonic series, nor about the controlling of excitonic properties in these van der Waals heterostructures. Only I want to mention that these excitons do dominate optical response, as it is seen, for instance, in this reflectivity plot. There you have the ground excitonic states, you have excited states, you have also another excitonic state that comes from the spin-orbit interaction split of bands. And in fact, you have relatively good agreement between the observed spectra and theoretical modeling based on this relatively simple Schrödinger equation. In addition to the optical properties, just to standard spectroscopy and also time-resolved dynamics, people actively study excitonic transport. And also in optical experiments, you can visualize how excitons propagate. And this, if I have time, will also be a short part of my talk. So now let us move on. Now let us speak about long-range interactions. Now let us speak about long-range electron-hole exchange interaction and exciton fine structure in these materials. So I would like to remind you with this very simple slide how the direct Coulomb interaction, the one which binds electron and hole together, works from the many-body physics perspective. So consider just, again, this very simple two-band model, conduction band, valence band. You have electron-hole pair. And now you can consider the interaction of these electrons with any of the electrons in a field valence band. And then because of this interaction, you can have a scattering. Then the electron in the conduction band changes the position. It's easy. Here are no occupied states. And the electron in the valence band actually goes to the only possible empty state that can be attributed to the motion of the valence band hole. And this, in the case of transition metal dichalcogenides, this process is related to the intra-valley scattering because both electrons stay in the same valley, and it is the main contribution to the exciton binding energy. Now let us recall that actually we are dealing with a two-valley system. We have one valley K plus and another valley K minus. And as I have already mentioned, say exciting the system with circularly polarized sigma plus light, I can create electron-hole pair, or I should say more accurately, electron and unoccupied state in this valley K plus. And now let me take into account the interaction of this electron with any of the electron in the other valley, something like that. The Coulomb interaction would be like this. But I will still take into account only the long-range part of the interaction, only the part that is related to the, sorry? To the part that is related to large distances, many unit cells. So each electron remains in its own value. We take into account this interaction, and actually the only process possible is the following. This electron from conduction band goes back to the valence band, but the other electron in another valley gets promoted to the conduction band from the valence band. And so you see the valley has changed, and in this way, the valley flipped and the polarization changed. Now this electron hole pair will emit sigma minus polarized light. So this is just a cartoon example how the long-range exchange interaction works in the excitons. Of course, you can do a more sophisticated theory. Actually, you can deal with this problem in many different ways. Back in the days, this problem was attacked from several directions. You can, for instance, just calculate the Coulomb interaction exactly as I explained here, the interaction between these and these guys, and calculate corresponding matrix elements. You can do another calculation. You can take into account that exciton is like dipole. It produces electromagnetic field, and then, as any dipole, it interacts with the induced electromagnetic field, and it will give actually the same result. You can make it using the Green's function technique. You can do it using the Maxwell's equation, and so on and so forth. You can do it diagrammatically, for instance, and you can calculate this contribution to the exciton energy related to the process I have described you: virtual recombination, virtual annihilation of exciton, and generation of exciton in the other valley or the different spins. So since we are dealing with optically active excitons and we are dealing with two states, sigma plus or sigma minus polarized, in the absence of any perturbations, they should be degenerate. So we deal with a standard two-level system. So we can describe bright exciton radiative doublet as a pseudo-spin 1/2, just like the electron spin. The meaning of the spin components will be, however, different. So SZ would give you the degree of circular polarization, but in plane pseudo-spin components will give you the degree of linear polarization. It is very much similar to the Stokes parameters and to the polarization density matrix of light. So for excitons, in principle, you can introduce also the 2x2 spin or valley, in our case, density matrix. You can introduce the Hamiltonian, and this Hamiltonian has a kind of Zeeman term. And this omega, it will depend on the exciton momentum, on the exciton wave vector, is actually a result of the long-range exchange interaction, which I have explained to you. And if exciton now propagates, this omega is non-zero, and as a result, the excitonic states will be split. In fact, they will be split into two linearly polarized states, one along the electron momentum, and another one is perpendicular to the exciton momentum. So in a more formal way, you can derive this kind of expression for the effective exciton Hamiltonian basis of sigma plus and sigma minus polarized states. And these off-diagonal terms, you see, they contain the second angular harmonic of the wave vector. And because they flip the polarization, you need to change the polarization from sigma plus to sigma minus. So you need to introduce or to remove the momentum component being 2. So these are second angular harmonics. And this Hamiltonian looks as an effective magnetic field acting on the exciton pseudospin. And the coefficient here has actually a very simple form. This coefficient depends on the exciton radiative decay rate gamma naught. It's the band gap of the material, or more precisely, the exciton emission energy. And there is also the exciton momentum in the denominator. If you look at this formula, it turns out that it is kind of non-analytic for small exciton momentum. And this is because the states of excitons with small wave vector, then the wave vector of exciton is smaller than the wave vector of photon, they are within the radiative cone. And that is why these states decay radiatively. And in fact, the coupling of excitons with induced field in that case would provide you the radiative decay. And that is why, in fact, the general expression for this exciton Hamiltonian or for this exciton self-energy is a little bit more complicated. But anyway, for practical purposes, you can forget this very small radiative cone and only discuss the excitonic states with sufficiently large wave vectors. And then these excitonic states are split, as I have already explained to you, in the longitudinal and transverse state. In the longitudinal state, it is linearly polarized along the exciton wave vector, so the microscopic dipole of the exciton oscillates along k, and for the transverse state, it oscillates in the plane, but perpendicular to the k. We have this effective magnetic field, and this effective magnetic field produces a lot of effects on the exciton dynamics. For instance, it acts as a driving force for exciton spin valley dynamics, and one can indeed observe it in experiments. Then you create excitons, say, by circularly polarized light, and then you measure depolarization. You measure the time, spin valley relaxation time in our case, at which exciton circular polarization would vanish. And I'm showing you here the results of our collaboration with our colleagues from University of Toulouse in France, who measured the exciton spin valley depolarization by using pump probe technique. So the points are the experimental data, and these curves are model calculations within actually the kinetic equation model for the exciton spin density matrix. And you can get reasonable agreement between the theory and experiment, depending a little bit on the parameters of the structures. It was about 10 years ago. The quality of samples was not very high. The scattering rates were probably a little bit too high, but nonetheless, you can observe exciton valley orientation. You can observe its relatively fast depolarization on the time scale of several picoseconds. And actually, this is the effect of exciton long-range exchange interaction, the exchange interaction between electron and hole. And this is one of the specific features of these transition metal dichalcogenides. You have very fast spin dynamics of excitons, but if you turn to the resident electrons or holes, so if you add doping and you will study the signals at long times, then electrons and holes show a very slow spin and valley relaxation. You see it could be on the orders of hundreds of nanoseconds in some cases, and in some cases even on the order of microseconds. And this is because to lose the polarization, you need to flip the valley and simultaneously the spin, and these processes are very slow. So for excitons, everything is very fast because of the long-range exchange interaction. Now, let us move on. So I have tried to convince you that, okay, it is something interesting. We can study the exchange interaction in excitons. And what would happen if you now add a little bit of electrons or a little bit of holes? And this in these two-dimensional materials, again, as we have heard already, it is quite easy to do so, because what you can do, you can simply use this 2D layer as a plate of a plate capacitor, and then you can have a top gate, and then you can control the doping density. So the first thing is that because of very high binding energies of excitons, hundreds of milli-electron volts, for any reasonable doping, the Fermi energies say on the order of several milli-electron volts, maybe 10, 20 milli-electron volts, the exciton binding energy is huge, and the Fermi energy is small. And that is why typically excitons should be very stable. There is no screening of the Coulomb interaction in that case. The screening should be dynamical, and dynamical screening is not efficient. However, what can happen is that this exciton can pick up one of the resident carriers and form a bound state, which is called a trion. There is another picture of the same situation, kind of more theoretical one, when people speak about exciton as a kind of mobile impurity in this Fermi sea that gets dressed by the Fermi sea excitations, and this is what is called now Fermi polaron, but actually back in the days it was suggested by Robert Souris, and some people also call it Souris tetron. So these trions are routinely observed in transition metal dichalcogenides, and they have relatively high binding energies. So typically the binding energy of the trion is something like 10% of the exciton binding energy. So it should be something on the order of 20 to 30 milli-electron volts in this case. And indeed, for instance, if you add some doping, you add more holes or you add more electrons, You can see in this experimental plot, you have the neutral exciton. In principle, you have some excited state of exciton. But more importantly, if you add holes, you get another line below the exciton, which can be associated to the formation of Chern. So you pick up a resident electron from the Fermi sea, and you get this free particle bound state. If you go to the n-doped case, you can see a doublet here, and again, it is the feature related to the Chern, and the fact that we have a doublet here is related to the specifics of the band structure of these transition metal dichalcogenides. I will try to explain it in a minute. So actually, it is not that easy, and there was a lot of debate in the literature how to describe this system properly. The point is that, of course, exciton can bind with any electron in the system. So before I go into this detail, I will quickly tell you that depending actually on the transition metal, whether it is tungsten or whether it is molybdenum, there could be just a single Chern line or a Chern doublet. Because, for instance, in the case of tungsten, you can have both intra and inter-valley interactions. So you have in principle two Cherns. The two electrons are in the same valley but with different spins, and two electrons are in different valleys but with the same spins, and you can typically see a doublet here. In molybdenum disulfide, the optical transition rules are slightly different. Actually, just the order of conduction subbands is different, and that is why there is just one Chern line here. Anyway, the question is how to describe this system properly. And this is a very simple idea, again proposed by Robert Suris back in the days at Ioffe Institute. You create the exciton. Now this exciton interacts with the Fermi sea. Let us assume that you have just a simple situation, molybdenum-based structure, so the bound state can be only with electron in the opposite valley. Otherwise, just the Pauli principle blocks it. Now you take into account this Coulomb interaction, and because of this Coulomb interaction, you create an electron-hole pair in the Fermi sea, something like this. And now you have a situation which can be described as a superposition of exciton and exciton plus electron-hole pair in the Fermi sea. Or you can rewrite this wave function in a little bit different way. You can consider this exciton plus electron as a Chern, and then you have also a Fermi sea. Very simple, so you can see, okay, it's almost like a Chern. There is some correlation with the Fermi sea. And indeed, if you discuss many of the phenomena, like shuffling of the oscillator strands between exciton and Chern, if you discuss photoluminescence, even if you discuss transport properties, these both models give basically the same result. Sometimes numbers slightly differ, but it is not a strong difference. The point is that we wanted to find a situation, then these two approaches, the Fermi-Polaron approach and the Chern approach, would give different results. And it turned out that it is possible if we start studying the fine structure of these complexes. Because you see, the Fermi-Polaron, or the Suris tetron, is actually a four-particle guy. It has exciton, and it has another exciton, another electron-hole pair. So it has an integer spin. On the other hand, the Chern is just a three-particle complex. You have just three fermions here, exciton plus extra electron, and it has a half-integer spin. And these states are very different in terms of the symmetry related to the time reversal. Indeed, for instance, if you deal with electrons or with the Cherns, you can never make any combination of two different spin states or two different Welle states that would be even at time reversal. Always time reversal brings your, say, spin up state to spin down state, one Welle state to another Welle state. Doesn't matter which linear combinations you take. However, for instance, for excitons, it is not so, because the spin is integer, and from these integer spin configurations, sigma plus and sigma minus, or momentum component +1 and -1, you can actually create the states that are linearly polarized, say X and Y polarized, that are even at the time reversal. So the time reversal doesn't mix those states. So what we can expect, if we deal with trions, then we can simply say that there are no low wave vector spin or Weyl dependent terms in the Hamiltonian, just because of the time reversal. In fact, k-linear terms, something like k times sigma, are forbidden by this d sub 3h point symmetry of the system, and the quadratic terms are forbidden by the time reversal symmetry. If we deal with excitons or Fermi polarons, then these quadratic terms are possible. So we have already discussed these quadratic terms for the case of just exciton. These terms control the longitudinal transverse splitting of excitons. So we decided to calculate this effect for the trions and to check whether it is indeed possible or not. And indeed it is possible. We have performed the symmetry analysis that tells that, okay, you have the neutral exciton, which is split into this longitudinal and transverse component. And if we describe the charged excitons, the trions within the Fermi polaron model, you would have similar splitting. So you can have it both in molybdenum-based TMDCs. Here you have just one type of Fermi polaron, inter-Weyl one. In tungsten-based TMDCs, you have two types, and they can in principle have different splittings, and there could be also a mixing between those terms. So using the symmetry approach, we can derive corresponding Hamiltonians, and then we can also find these splittings as a function of Fermi energy and as a function of momentum of this particle using the microscopic theory. I will probably not go into much detail. I will show you just one formula. This is for molybdenum-based material. The splitting is proportional to the exciton splitting with a factor which is basically the Fermi energy divided by the trion binding energy. So you can say that the Fermi polaron inherits the splitting from the exciton, and that is why we have this small coefficient. So the theory is valid for not too high Fermi energies, and the Fermi energy is much smaller than the trion binding energy. Otherwise, these trions and Fermi polarons becomes basically screened. In tungsten-based materials, in tungsten-based TMDCs, the situation is a little bit more complicated. Actually, the factor that plays a role here is now the ratio between the Fermi energy and the splitting between inter and inter-Weyl trions. So this contribution is expected, at least in the theory, to be the largest. So we propose to measure these splittings and indeed to justify the Fermi polaron approach, or if the splittings will turn out to be zero, then probably the trion approach would be more accurate for these systems. But anyway, the correlation between trion and the hole in the Fermi sea brings about this many-body complex, the Fermi polaron complex, makes it possible for trion to have this longitudinal transverse splitting, which is inherited from the exciton, so it contains the factor like Fermi energy divided by some characteristic trion energy, the binding energy, or the splitting of the trion states. And it may also be important for studies of the Weyl physics of trions and Fermi polarons. So how much time do I have?
Actually, you have few minutes and then 5 minutes for questions.
Okay, then I will go very quickly because now I'm going to quite shaky grounds. I want to speak a little bit about exciton transport in moiré lattices, which is mediated by the long-range exchange interaction between electron and hole. So the physics is very simple. We have again heard a lot about moiré physics, and basically if you put one TMD layer on top of the other, then you can create an effective superlattice potential for charge carriers and for excitons. I will not go into any theoretical details about it. This potential is strictly speaking not periodic. There could be a disorder. And in principle, this potential is quite deep. The depth, at least for some TMD-based materials, the depth is on the order of tens or hundreds of milli-electron volts. That is why excitons can be localized in this potential minimum. And quantum mechanical tunneling is actually strongly suppressed in that case. However, because of this long-range exchange interaction, you can have a kind of long-range hopping between the localization sites. You can also interpret it in a form of Förster-like coupling. So the exciton at one site recombines, and it creates the electromagnetic field that propagates, and then it creates the exciton at the other side. You can map this problem just to a problem of dipoles interacting via the electromagnetic field, and you can, of course, easily calculate the spectrum. Without going into any detail, you will get, again, two branches. You get the transversal branch, which is localized. It is dispersionless if you disregard the quantum mechanical tunneling. But if you consider a longitudinal branch, it is linear in the wave vector, very similar to what I have shown you before. And effective propagation velocity is given by the speed of light multiplied by a small parameter, the exciton radiative decay rate to the exciton resonance frequency. And again, this linear dispersion is valid in a quite large range of the wave vectors. Apart from very small momenta here, then excitons become optically active. And then it turns out that even if the excitons are localized in these moiré lattice, some of these longitudinal excitons can propagate. And then depending on the disorder, you can imagine different scenarios. For instance, it seems that in that case, you can have a hopping transport, say phonon-assisted, but with the diffusion coefficient, which is proportional to some power of the temperature. The power law temperature dependence rather than with the exponential one. And this is just because of the long-range hopping in that case, because again, the coupling between sites decays something like 1 over r to the cube. This is this dipole-dipole coupling I have mentioned as an origin of the effect. So I think that I have run out of time, and for the sake of showing the last slide, I will finish here. So thank you very much for your attention. And of course, Boris, greetings from all of us here at Ioffe, from all your colleagues and friends. And I am very grateful to you for our long-range interactions. Thank you.
Okay, all questions are supposed to be heard to the speaker. So question, please. Yes.
So you can hear me, I guess.
Yes, I can hear. I can hear you.
Okay, yeah. So if you keep pumping the system, you populate one exciton per site in general. So what do you expect for the transport for the excitons?
Yeah, I think that this situation would be very different. So of course, the model I have shown here and our preliminary results are related to a kind of single exciton problem. Then you have more or less one exciton per lattice, and the interactions between excitons are unimportant. If you pump to the situation, then you have one exciton per site. I expect that the physics could be very different because the system could be strongly interacting. Maybe there could be something like superfluidity. Maybe the main contribution to exciton transport would be related to the kind of vacancies in that case, to some sites that are not occupied by the excitons. But really, I do not know. I think it is an interesting question to study further.
So another very basic question is that the excitons here carry permanent dipole or they don't?
It depends. Let me say the following. It depends whether you consider, intralayer or interlayer excitons.
Which
So
one are you considering?
so the theory applies to both of those. So for interlayer excitons, the coupling to electromagnetic field is stronger just because of strong overlap of electron and Hall wave functions, but they do not have a static dipole. Interlayer excitons, they do have static dipoles, so they have stronger interactions, but on the other hand, the oscillator strength is smaller, and the coupling with electromagnetic field would be smaller, so this branch in the dispersion would be less steep.
Yes.
So for your Fermi Polaron pictures, do you have some kind of numerical estimations of what is potential mass of this Fermi Polaron?
Okay, it's a good question. I'm sorry for not having the slide at hand. So for the reasonable parameters, the effective mass of this Fermi Polaron would be something between the Chern effective mass and, let us say, B exciton, two exciton effective mass. So for the reasonable parameters of transition metal dichalcogenides, it should be something between say free electron mass and probably 1.5 times free electron mass.
It is much heavier than trions in some sense.
In a way, yes, but not much. I mean, there is no parameter, at least for the range of densities we consider.
Thank you.
More questions? Yes.
So I thought for Fermi Polaron problem, there are two branches, an attractive one and a repulsive one, and it's attractive is more like a trion, and the repulsive is more like exciton. Is that right?
Yes, it is here. This if you increase the Fermi energy, the repulsive one will emerge from the exciton, and the attractive one from the trion, right?
So that's why there's no really controversy. You said that it's not clear which one is you have, but you have both, right?
Yes, yes, we have both. The question is how to describe what you see in the optical experiment. And in fact, it is a bit of tricky problem, because the question is to which extent the correlation between the trion and the hole in the Fermi sea is kept or not. And this is something which people explore now, and this is something which is not entirely clear. But basically, yes, if you go with the Fermi energy to zero, then basically you end up with this few particle approach. Then Fermi polarons and trions will not be distinguishable.
Yeah, please.
In a picture of that localized exciton in the moiré lattice, it's the potential well is like a harmonic oscillator. So do you expect the degrees of freedom, like there are multiple levels inside of this harmonic oscillator potential well enters in the story?
In principle, yes. So our model is, of course, very simple one. We consider only the ground state of this harmonic oscillator trap. Actually, the higher states have small oscillator strength, at least in theory. That is why probably in terms of this splitting and this linear part of the dispersion, probably it is sufficient to account for the ground states only. But, well, in principle, you are right. There are excited states, and they can affect the dispersion. There could be some anti-crossings here. You are right.
Yes.
I have just one last question. So these are optically excited excitons for the transport setup that you study. If I guess that Foster channel is turned off if the excitons are in equilibrium, right? If like I use gating to create the electron hole layers rather than generating by photons.
It's a good point. I think that well, if we discuss the homogeneous system, then of course there will be no diffusion. There is no direction for excitons to travel. Also, if you create, say, optically forbidden excitons, the excitons with zero radiative decay rate, say spin forbidden excitons, then the situation will be, of course, different, and this mechanism will not work.
Okay, with this, thanks very much. Thank you.
Thank you. Thank you.
Okay, and now, sure you were muted.
Yes, I hear you. I don't know if you hear me.
I can hear you, you are not muted, so sure, Alexander Grosberg, Coulomb physics, and with neutral particles. New York University.
Okay. Let me share my screen. I'm not sharing yet, am I?
Oh, you should
hit twice. There is something else.
If you share screen, you share.
Okay.
You don't
Yeah.
want-
Okay.
Yes, now start working. Yes.
Yes.
Now we see everything. So go to slideshow and
Yep.
yes,
So we should be in business now.
yes, well in the business. Yeah, your time.
Very good. Okay, thank you. Thank you, the organizers, for giving me the chance to take part in this exciting meeting, despite the unfortunate circumstance that I committed to be in a very different half of our globe before Alex and Brian sent invitation to me. So happened that I cannot be with you in Minneapolis, but thank you for allowing me to speak remotely. So all of us know how Boris easily switches from one field of physics to another field of physics, which is charming and sometimes amazing. Thing to be related to Coulomb interaction. So therefore, I decided to tell you a little story, which I think is quite, it is very simple, but I think it's quite charming, and I hope that you find it so. So I decided to start from something that is the least controversial that you can imagine, and I suggest that this equation must be like this. It is the least controversial representation. However, we all know that phi doesn't have to be electrostatic potential. It may also be something else. And that's what I want to tell you about. So let's consider, okay, now my computer doesn't want to move from one slide to the next. That is the problem. Okay, so let's consider this experiment, which actually I showed when I was speaking in the colloquium in Minnesota several years ago, in 2019, in fact, before the COVID. So in this experiment, what happens is these particles that you see on the screen, they are catalytic particles. Because they catalyze some chemical reaction, they move in the way which is far from equilibrium. They represent some sort of an active system. They violate detailed balance, and many interesting things happen. But I want to concentrate on something super simple that is related to this system. So you have this many colloidal particles sitting in the liquid and catalyzing chemical reaction. So what you don't see is you don't see some chemical components, in this case, hydrogen peroxide, that diffuses towards or away from these particles. And I want to discuss what happens about this. So this is a very simple, naive picture here, which all of us know. This is, in fact, the Smoluchowski model of diffusion, when these green particles here, they diffuse around, and there is certain concentration of these particles. If they are absorbed on this red ball in the middle, then the concentration, steady state concentration profile goes like this. This is quite trivial. Everybody knows this, of course, but I want to point out that there is a desirable 1/r Coulomb-like profile, which is trivial, which is obvious, but yes. So let's see where it brings us. So let's do a little bit more. Instead of particles that are absorbed on the red ball, and which cannot continue forever, of course, let's imagine that in infinity we have the supply of some fuel molecules, A, which diffuse towards catalytic surface, and then catalytic surface catalyzes transformation of fuel molecules A into exhaust molecules B. Then you have chemical reaction happening on this surface, and you have this simple construction where you have 1/r type concentration profile of fuel molecules and similar 1/r concentration profile of exhaust molecules with their respective diffusion constants. And you have this chemical rate that is with corresponding rate constants of catalytic reaction KAB and KBA. So this system is supported out of equilibrium as long as in infinity you have the supply of this A and B molecule, fuel and exhaust. Very simple. Okay, so this is just, if you exercise in algebra, you find that this chemical current is given by this formula in green frame. And you see that, of course, this chemical current becomes zero if concentrations in infinity correspond to chemical equilibrium, and the rate is given by what fits in the denominator. Again, very simple, nothing exciting here. But now imagine that you have two such catalytic particles. So here I am afraid that I asked my computer to do more than it wanted. My idea was that this yellow background will have yellow color in some gradient. And there is some gradient of color, but probably it's impossible to see. In any case, please imagine that there is that this ball in the middle catalyzes the reaction. Of course, it creates a gradient of this concentration, and the second ball finds itself in the field where surrounding concentrations are not uniformly distributed, but there is some concentration gradient. Now, if a particle sits in concentration gradient of some molecules, then there is a phenomenon called diffusiophoresis. So this diffusiophoresis, you can think about it in the framework of standard Onsager linear response theory, and there is trivial relation that velocity at which colloidal particle moves in the presence of gradient of some concentration is proportional to the gradient linear response. Again, very simple, but importantly, this coefficient kappa can be either positive or negative, depending on how surface interacts with these molecules whose gradient is present. This, of course, means that two catalytic balls like this interact with the force, which is proportional to 1/r², like a Coulomb force. So we can go a little bit more in a little more details. We can describe this force in a little more details, starting, of course, from this blue framed formula, which is the distance dependent part of the surface energy of these two molecules. And here, of course, we assume that diffusion of colloids is pretty slow, such that at the given distance between two colloids, surface properties come to equilibrium, and therefore we can operate with the equilibrium surface tensions. These primes indicate a derivative with respect to concentration. And these derivatives, in the simplest case, they are given by this formula where this epsilon tilde is the difference between energy of the, let's say, A particle, in this case B particle, difference between energy of the particle close to the surface and in the bulk, and this gives surface energy, and the derivative will give you this extra energy. So this is all quite trivial. If you go through these manipulations, you eventually discover that this force is controlled by this expression in the brackets. So the point that I want to make is this expression in the brackets can be either positive or negative, depending on how these particles interact. Fuel particles A and exhaust particle B, how they interact with surface of my catalytic colloid, that determines the sign of force. So you can make this little phase diagram, which, depending on this interaction parameters, indicates when force is attractive and when force is repulsive. Again, there is nothing deep or nothing complicated. But let us see where this leads us. Of course, the more interesting version of Coulomb interaction happens when there is screening. So is there something analogous to screening for my colloidal system, where two colloids interact with Coulomb-like force, but is there something analogous to screening? In order to see that, let's imagine now not two colloids, but the crowd of catalytic colloids, many of them. So there is this letter phi of R is a concentration of catalytic colloids. There are many of them, and I characterize their presence in terms of their concentration. So phi is basically the unitless volume fraction of these colloids. And then the rate of both reverse and forward reactions on the surface of every colloid will be proportional to the number of catalytic colloids that are present. And therefore, in coarse grain sense, or the distance is larger than the distance between this colloidal catalyst, you have these two diffusion equations. Again, fuel molecules diffuse with their own diffusion coefficient, and exhaust molecules diffuse with their diffusion coefficient, but with the rate proportional to the number of colloids, concentration of colloids, you have a chemical reaction that occurs on every colloid surface. So in fact, this suggests that the key player here is a quantity which I call the field of chemical imbalance. So we decided that this chemical imbalance is non-zero in infinity, but now it will depend in some way on the place, on coordinate. So in steady state, if you forget about time derivatives here, forget about time derivatives, you study the steady state distribution of fuel and exhaust molecules, and you discover that, of course, this steady state distribution describes this chemical imbalance function in this familiar form, where screening radius is given by this formula. So the screening radius is, of course, inversely proportional to the square root of concentration of these colloids, which is absolutely not surprising because the Debye radius, of course, depends on concentration of colloids in the same way. And there is this factor which is controlled by rates of reactions and diffusion coefficient. Now I want to emphasize that this is not, although there is 1 over r square force, which is similar to Coulomb, the nature of this screening is not quite the same as in Coulomb system, because in Coulomb system, the nature of screening is closely related to the fact that there are charges of 2 different signs. Here in our system, as long as we have only one type of these catalytic colloids, we have only one type of charges. And so that is the difference. So let's see where it goes. So let's consider an example. Here is an example, and suppose in 3 dimensions we have these catalytic colloids, a crowd of catalytic colloids confined in some osmotic bag. They do not, osmotic bag, I need osmotic bag in order to prevent these catalytic colloids from diffusing fuel. In infinity, as before, we have this psi of infinity, which is the chemical imbalance function, chemical imbalance potential, which is non-zero in infinity, and therefore fuel molecules diffuse from infinity while exhaust molecules diffuse to infinity. And then what happens? Then what happens is, in fact, over the distance of order psi from the surface, this psi chemical imbalance gets screened. So chemical imbalance only penetrates into this osmotic bag by the distance of the order of the screening radius. And inside over most of the volume inside, interestingly, inside you don't have this chemical imbalance, but you do have both fuel and exhaust. Both of them successfully diffuse inside. The only thing that happens is inside they are basically in equilibrium. The relation between concentration of A molecules and B molecules inside this concentration of A molecules, which is green, which is white thing, blue thing, and a B molecules, which is yellow thing. The concentration, these 2 concentrations are in balance. They are in equilibrium with each other. And therefore, chemical current inside is 0. It is screened out, and therefore, opposite to what I said to you in the beginning, these colloids inside do not interact. There is no, well, they may interact for some other reasons, but they do not interact for this diffusion theoretically. So it is a bit disappointing, it seems, because, okay, so we discovered that basically nothing interesting happens. But let's consider something more realistic that I told you already. So more realistic, in fact, these colloids usually are heavier than water, and therefore they sit at the bottom of the container. So therefore, let's consider what happens if we have a sort of quasi two-dimensional system in which colloids are sitting at the bottom of the container within some, as people call it, gravitational height, which corresponds to gravitational potential energy being of the order of thermal energy. So again, they are confined by an osmotic bag, and in infinity, we still have this psi of infinity, which is our chemical imbalance. And it seems that, okay, so if you take a really shallow container and say that this container is so shallow that the system is two-dimensional, then yes, we know that there is Coulomb business in two-dimension is different than three-dimension, but as far as the physics of this screening concerned, it's basically the same idea as in three dimensions. You only penetrate, your chemical imbalance only penetrates a short distance of the order of screening length into the pancake of colloids, and colloids in the middle, again, don't fill in. So, and by the way, this effective screening is roughly estimated like this, where psi is given by the formula that I gave you before, and big H is the depth of this container, and little h is gravitational height. This is not so important. I do not concentrate on it. Instead, I want to say what happens if the particles live actually at the bottom of a deep container. In that case, something interesting happens, because in that case, of course, delivery of, again, we have this chemical imbalance far away in infinity, but delivery of both fuel molecules into the system like this, and delivery of exhaust molecules away from the system like this. This does not happen in two dimensions. It happens in three dimensions. It happens, strictly speaking, not in full three dimensions, but with half a space. But basically, most important, it goes through three dimensions. And when it goes through three dimensions, then the solution of my screened Coulomb equation is very different. And there is no screening, basically. And now, finally, my colloids in the middle do interact with full force, which is proportional to 1 over r squared. And now I remind to you that this force may be attractive, or it may be repulsive. And so if the force is attraction, then of course the colloids will clump together and form some, well, in a really steady state, they will form one condensed group in probably at shorter time. They will form some smaller clumps. But if the force is a repulsion, then these colloids in the middle will form a Wigner crystal, filling the whole bag. So that is what will happen if we have sedimented to the bottom catalytic colloids living in sufficiently deep, well, not necessarily very deep, but sufficiently deep container. So this is basically the end of my story. I have to tell you that the story that I presented to you is basically this paper, my paper with my friend Itzhak Rabin. But other people, particularly Ramin Goleshtanian and his group, they analyze this Coulomb-like behavior in great details in many examples and so on and so forth. So I provide here a reference if you're interested. And of course, these people are serious people. They don't stop at having, they are not interested in simplicity. They don't stop at having catalytic colloids of one kind. They have catalytic colloids of two or sometimes more types, and therefore they generate incredibly rich phase diagrams like this. I do not want to tire you explaining all the details, but you see that there are blue particles. These particles are not my fuel and exhaust. Fuel and exhaust is in my pictures exists in the background. And these particles are two types of catalytic colloids. Sometimes they attract, sometimes they repel, and you see that they form a variety of various structures, all driven by this quasi-Coulomb interactions. So this is the paper by Ramin Goleshtanian, Sriram Ramaswamy, and their co-authors. This is the end of my story. I want to thank the organizers once again for organizing this event, well-justified event. I want to thank the organizers for allowing me to speak. I want to thank everybody who listened for your attention. And most of all, I want to thank Boris for, as I wrote here, for a friendship, for many illuminating physics lessons in various places, even sometimes in the office at the blackboard. So to conclude, I just want to show to you a few pictures of Boris in his preferred environment. And I think that there is no doubt that in all of these pictures, Boris is thinking about Coulomb interaction. Thank you.
Sure, thanks very much. Boris?